Welcome to Dueling AI, self-play reinforcement learning with a custom Pong engine. Before we get started, I'd like to say that this is a supercut of a series that I released a couple of months ago as a multi-video YouTube series. The content is exactly the same. This is just out here for people who prefer to see one long video and be able to watch that continuously and not have to bounce through a series of different videos. So I'm really just trying to accommodate everyone's preferences. It's again exactly the same content. If you'd rather watch a video series, I will drop the series link in the video description. For this supercut, I have chosen to leave all of the transitions, the beginning and ending of the videos alone, because I have different GitHub links for different sections of the video. And if you don't have those verbal transitions, you won't know which section which code goes with. So it is stitched together from a bunch of different videos that will show. If you like this format, drop me a comment. If you hate it, go watch the one that's, a series, and that'll be in the description. So let's talk about what we're actually building. So the goal here is to set up a self-play algorithm with Q-learning, and we're going to do that in our own custom Pong game. So self-play is a really cool concept that's basically letting an AI agent play against itself. So if you've looked at all into programs like AlphaGo, it didn't play against a curriculum. It didn't learn by playing against humans or by saved data. AlphaGo basically just took the game of Go, took the basics, the rules, and learned by playing against itself. So what we end up doing in these types of environments is we're going to train an agent by going in and allowing the agent to play against itself at first. And then let's say we're 100 episodes in, we're going to let it play against the previous version of itself. 100 more episodes in, we're going to let it play against the two previous versions of itself. And over time, we're going to build up a sort of stable of greats, the best previous versions of itself for it to play against as opponents. And the goal of this series is really to focus on that self-play architecture. If all you want to do is learn how to conquer Pong using AI, there are other courses out there that are going to cover that, and probably be a little bit of a simpler intro. This is much more taking Pong. We're going to write our own version of it, and we're going to use that as a platform to go learn about how self-play works in a reinforcement learning context. So the first thing we're going to do to get started, we're going to build a custom Pong environment with a basic bot that can play against a human or an AI. So the bot is going to be a paddle follower, basically, or a ball following, logic with the paddle. When the ball goes up, the paddle goes up. When the ball goes down, the paddle goes down. We'll build an easy and hard version of the bot in order to provide both something that we can quickly measure progress against, and then something that we can, measure a more advanced agent against, something that very seldom misses. And then something that I've wanted to do for a long time is to be able to compete against my own AI agent. So since we're building this environment ourselves, there's absolutely no reason that we can't build it in a way that a human can play as one of the sides. So that's absolutely what we're going to do. By the end of the series, what you're going to have is a custom Pong game that you can either have you on one side and a bot on the other, or a bot on one side and the AI on the other. Any mix-up of different opponents that you'd like to have there, AI versus AI, bot versus bot, you versus bot, you can set that up and it will support that. This is all going to be done in Pygame. It was the simplest way to build something that integrated well with our process. After we've built a game, we're going to train up a single-sided AI. And this is really just going to be an easy way to do some basic validation that our training steps are working. So doing self-play definitely adds some complexity. There are a number of different ways that the agent can spiral down into failure in a self-play scenario that are not applicable in a non-self-play Q-learning setup. So we're going to keep it simple, and we're going to start by just letting a single AI agent play against one of our bots and make sure that nothing fails, that we get at least some basic learning, and we're not doing anything, simple for mistakes that would tank us in a more complex environment. After we've got it working in a single-sided way, we're going to start training the AI agent against itself. We're going to let it play both sides of the board, and as it goes, it will get an increasingly more challenging opponent because it in itself will get better. We will build up that list of past great versions of the AI, and it's going to get a lot better. It'll get better as an opponent, and it will get better as the primary player. And then at the very end, like we said, you're going to be able to play against your own AI. We will be able to set this thing up so that you can be on one side of it and the AI can be on the other, and or you can watch the AI beat various bots. You can even get creative and code up your own separate bots and see if, how difficult you can make them and how well the AI generalizes, because that's really what we're going for here. We're going for the AI being able to learn against itself in a way that still generalizes against opponents that aren't it. And that can be a challenge. That's one of the reasons that we're talking about this topic, is it is an incredibly powerful way to do this. But it is definitely, there are some extra challenges to doing it. Other things that might be worth paying attention to. So I'm an AI enthusiast. I am not a researcher. Some things may not be perfect. I do not claim to have a textbook build out of any of the algorithms that we're talking about. They work well. The project has been a lot of fun, but again, I do not do this professionally. This is a coding walkthrough for a specific project. It is not a complete course. I hope you'll learn a lot from it. I hope you enjoy building it out, but it's not going to be, you're not going to walk away with a college course's level of understanding after this. If you need help, I will have a Discord link in the video description. And if you are interested in reinforcement learning, robots, etc., check out my other videos. There's a lot of really cool stuff out there. For things that I did not remember to put on this slide, I do want to talk for a moment about the hardware and tooling you're going to need to build this out. You will need to have a good knowledge of Python. You should be comfortable working in a Python environment. You should be at least slightly comfortable with reinforcement learning as a topic. If you have never touched reinforcement learning before, you probably want to go ahead and maybe I'm going to have an intro course as well linked in the video description. If you've never done RL, go look at the intro video or take one of the many other intro to reinforcement learning courses out there on the web. Jumping straight into building your own environment from scratch and doing self-play is going to be a challenge. This is a code-along series, so you will still be able to build it out, but you may not understand everything, and that might be a little bit discouraging as you're just getting started. So, good Python knowledge, moderate knowledge of reinforcement learning, light on the math. From a tooling perspective, you will need to have Python installed, obviously. You should be able to do this on Linux or Windows. I'm using Linux. There should be no reason you can't do this on Windows. You'll need to be familiar with pip and the ability to create a Python virtual environment. I'm going to be using Conda, but you can use VE. And then finally, just any editor that you're comfortable with. You will see me using NeoVim in this series. You do not have to use NeoVim. Use what you like. You're going to be a lot more effective with an editor and environment that you're comfortable with than you are trying to mirror mine. Now, all that said, let's take a look at what we're actually going to be building with this. So I'm going to run the Pong game. And what we're seeing on the left, the purple paddle, is my hard bot. So it's a pretty simple ball following algorithm. You'll notice what it's basically doing is trying to line up with the ball, not in the smoothest way possible, but it does work. The green paddle on the right is the AI playing. And something that's kind of ironic about this is the AI almost plays in a little more of a human way, whereas my bot on the left is clearly playing in a very erratic manner that I would associate with my own relatively poor static coding there. But yeah, our AI bot actually looks like it's doing something kind of cool. And again, very human-like as it's learned without human input. For metrics, we are going to be using TensorBoard. You can see I'm running that here. I'm going to exit out and hop over to our TensorBoard display. So at the end of this, you're going to have some good metrics around the training scores for the checkpoint policies and latest policy. You're going to have, evaluation scores tracking against the hard bot. You can see in the demo that I'm running here that the hard bot almost never misses. So you can tell that, the fact that we're at a score of 4 versus 2 against something that never misses or very seldom misses is actually pretty impressive. So you'll see that that success is actually just approaching 0. And you'll see that it succeeds. It hits that sort of max success right around the 1.3 thousand mark. You can continue training for a while longer, and it will get, in some cases, better over time. Sometimes the policy will actually decay a little bit. That's something you can play with. From a hardware perspective, you can run this on something as light as an RTX 3060. It is going to be important to have some kind of GPU on your machine. But it doesn't have to be anything particularly powerful. Just if you're trying to do this on pure CPU, it's doing image processing. It's taking pictures of this screen, of this Pong game, and attempting to process and work with those. So doing this without a GPU is going to be really, really slow and very difficult. So some kind of GPU, it can be a laptop GPU, it can be an older desktop GPU. I've run this on a 3060, a 3090, a 5090. Obviously, the nicer cards do better, but they're not infinitely better. It's not like if you have a lower end graphics card, you can't do the project. You definitely can. And with that, I think that's most of what I wanted to cover in the intro here. Again, I'm going to leave all of the transitions in. Oh, and you will find in the video links to GitHub, not just for the whole project, but you're going to find tags that are labeled part 1, part 2, part 3. So when you land in a part of the video, you'll be able to go and find the associated code for it. If something I'm always going to recommend is to try to take the time to solve any problems you hit yourself. You're going to learn more, you're going to do better if you can take the time to solve those things on your own. But if you hit a point where you just can't solve it, you'll find links to code for all of the various parts of the series in the video description where you can get to those. So yeah, I hope you have fun building this. It was an awesome project for me to make, and I will see you in this next part of the video. Welcome to part 2 of the Dueling AI series. We are going to, in this video, go ahead and get started on the environment build out, both in the sense of setting up our Python environment and building out the actual Pong environment. So let's get started. I'm going to go ahead and call this Dueling AI Pong, or our lesson. You may call this whatever you'd like. And I am using Conda. So I'm going to do a Conda create -n Dueling AI Pong. And I would like to note, if you are not using Anaconda, that's just fine. I think I mentioned this in the last video, but even if you're not using Linux, that's fine. Use what you want to here, as long as you are capable of creating some kind of virtual environment for your Python to live in, and we're going to be using Python 3.12. You can also probably use different versions of Python, but I would recommend sticking with what I am using. All right, so let's do conda activate, dueling AI Pong. All right. And the first thing we're going to do is get a requirements txt out there. And we are going to need pygame, numpy, opencv python, and I'm pinning to a very specific version for this one, tensorboard, which we'll use for logging and monitoring. And then you are going to need PyTorch. So I'm going to be pulling PyTorch down with CUDA support. If you go to their website, they're going to have the right steps for CUDA for your platform, or ROCm or whatever it's going to be for your GPU. Without CUDA support, it will not run on the GPU and it will be very, very slow. So take the time, look up your platform, and get the index URL. So I'm going to say extra index URL. For me, this is download.pytorch.org/WHL/C118. And I'm just going to make sure that is the whole thing. All right. And then from that, we're going to pull torch, torch vision, torch audio, and save. To install a requirements.txt, it's pip install -r requirements.txt. And the problem here is that I need a double equals. And we're now installing some of the NVIDIA packages we need. All right, and that pip error is perfectly fine. That's just saying that, hey, there are some dependency conflicts. We should be okay. All right. Next up, and this is not something you need to do unless you are planning on tying your build or your run command into some kind of shell script. This is very custom to my workflow. Anaconda 3, etc profile.d, conda.sh. Basically, I'm setting up a shell script that I can use to kick off our Python scripts later. Conda activate, let's see, what did we just call this? Dueling AI Pong. All right. So let's go back into build.sh. And I'm just going to call this Dueling AI Pong, and then python./main.py, which is going to be our first file. All right. Again, for that last part, the build.sh, not necessary unless you want to be able to kick this off from a shell script. If you're using an IDE and you're just going to use whatever key combo you would use to run a Python file, that's totally fine. So let's go ahead and we're going to create a main.py and start with our basic hello world and just make sure everything is wired correctly. And it is not. This is why we test things. Okay, build.sh called, and hello world successfully executed. Cool. We're getting somewhere. We are going to go ahead and create the game.py this is what will have all of the actual game assets in it. And I'll just close that out so we can see things a little bit better. All right, so let's just kind of start with some of the structure. We're going to say import Pygame. Pygame is going to be necessary. We're going to need to import sys. We'll need quite a few imports, but I'm going to save some of them for when we actually need them. So let's start by just declaring our class Pong. And we don't really need a whole lot from gym, but let's go ahead and pull it in as a gym env. So we're going to import gymnasium as gym. So let's say class Pong gym.env. So we're going to inherit from that. And then we will need to define our init method. So init, and some of the basics here, I actually do need self there. I'm going to do window underscore width is equal to 1280. Window height is equal to 960. A note on these widths and heights. So these are in pixels. I am using a 4K monitor. If you are using 1080p or 1440p, you may want to scale this down, but it will affect other game dynamics because we're going to be putting in sizes for things like the paddles and, ball speed will be in pixels. There's a lot that actually boils down to the pixel count. So if you are on a smaller screen, maybe cut it in half and then use that same cutting in half for all of the measurements. Again, building this for what I have on hand. So we're going to do window width 1280, window height 960. FPS is going to be 60. Player 1 and player 2. We're basically going to be defining whether player 1 and player 2 are bots, AIs, humans, what are our players. So I'm just going to make the default player 1 AI, player 2 will default to bot. Render mode will default to RGB underscore array. So in other words, not displaying to screen. We'll need step repeat. So basically every time an action's taken, it's going to repeat 4 times. That's pretty standard in Pong environments. Bot difficulty will be hard by default, and AI agent will default to none. All right, and I know we just typed a whole bunch there and probably didn't make a whole lot of sense. That's okay for now. We just needed some variables. We'll use most of them later, or all of them later, most of them soon. So the first thing I want to do is just do some basic input validation. So for P in player 1, player 2, if P not in AI bot human, we want to go ahead and raise a value error. All players must be AI, bots, or humans. Okay, doing some input validation. We want to go ahead and set up our self.window width will equal window width. Self.window height is equal to window height. And self.step repeat will be step repeat. Self.render mode will be render mode. Again, just setting up some of the basic variables here. And And then something we do need to set is we need to make sure that if render mode is not human, so if render mode is something that's meant for the agent and not a person, then we actually need to set an OS environment variable. So let's come up here and let's import OS. And then we're going to do if self.renderMode is not equal to human, then os.environ SDL video driver is equal to dummy. And what this is going to do is this is going to tell Pygame, it's basically going to null route the video driver and will stop it from displaying on the screen, which is important. Like we don't want to, you don't want to sit there and actually display the game while you're training, because training will go vastly slower if your computer has to actually show the game being played. So let's go ahead and do pygame.init, pygame.display.set caption. We're going to do Pong. And let's do some basic testing here. So at this point, we should be able to come over to our main.py, which should no longer just be a hello world. It can be a real file now. And we're going to do from game import Pong. And then we'll do env equals Pong. Render mode. Oh, I don't need that in quotes. That is wrong. Render mode is equal to human. We'll do player 1 as human. Again, there's no logic yet. Player 2 will be bot, and bot difficulty will be easy. And then there will be no AI agent. All right, no module found gymnasium. Did I? Because I did not include gymnasium in requirements.txt. All right, let's fix that. So I just added gymnasium to my requirements.txt. Over here, I can conda activate Dueling AI Pong and pip install -r requirements.txt. Again, all right. We now should have gymnasium. Let's try again. All right, we have Pygame successfully not doing anything because we haven't actually done anything with it, but Pygame is there and the basics are wired up. I'm a big fan, by the way, of running things frequently. You know, I would rather not get thousands of lines of code in and then find out that there's a problem. I'd much rather find out as early as possible that that something is wrong in our setup here. So, all right, let's go back to editing our game.py. So we'll need a few things. We'll need a clock. So pygame.clock will be equal to pygame.time.clock. And we're going to need a screen. So self.screen is equal to pygame.display.set mode. And we will do window width. Or actually, let's be consistent. Let's do self.window width, because that's what we'll be using in other places, and self.window height. And keep in mind the double parentheses there. You do need them. Self.fps is equal to fps. And then we get into our colors. And you can make these whatever you want. My wife picked out the purple and green for me, and I think it looks really cool. But so just to match my purple and green, you're going to do self.player1 color is equal to 50, 205, 50, and self.player2 color is equal to 138, 43, 226. And if you want something different, again, pick your own. It's your game. You're coding it up. Just go find a color picker and find the RGB values and plug them in here. We're going to do a paddle height, self.paddle height of 120, self.paddle width of 20, because again, paddles are side to side. We're going to do a bot difficulty. So self.bot difficulty is going to be equal to bot difficulty. We'll do a font. Self.font is equal to pygame.font.sysfont. And this will be none and 70. This is going to be a fairly large, it's not huge, 70 pixels. Self.announcement font. This will be for things like the, you won, you lost, that kind of stuff. Pygame.font.sysfont, and none and 150. All right, we're almost done with the init method. So we will be doing self.player1 is equal to player1. Self.player2 is equal to player2. This is just a whole bunch of boilerplate. And then we need an action space. So self.action space. This is a gem concept. So spaces.discrete 3. So what this basically means is we can take 3 discrete actions, which will be 0, 1, and 2. And the reason that we want to define this as an action space, the reason Jim has it this way, is that when you are using this environment in code that requires, that needs to know how many actions you can take, you can call your action space variable and it's going to tell you. It also has the ability to randomly sample an action. So, calling an env.actionspace.sample will give you a 0, 1, or a 2. That's the advantage to having this over just saying, action space equals 3. We'll do self.ai agent is equal to AI agent. And then finally, we're just going to give ourselves some logging here. So I'm going to say creating new Pong game. Let's do players, and we'll do player 1, and player 1. I don't need those curly braces. Okay, and player 2 will be player 2, and then bot difficulty is equal to self.bot difficulty. And this is just to, get a little bit of information out of our environment. When we need to know what's going on, like, hey, am I playing the bot difficulty I thought I am? If I expect to be playing an AI versus a human, is that what's happening? You want some of these things. We're going to declare a reset method. And for now, I'm just going to say pass. We'll add some content to it later. And then our last line of the init method is calling self.reset. All right. Oh, and reset needs a self. Okay, let's run this one more time. And we got our little window popped up, which is all that I'm expecting at this point. We've created a a display, and that display pops up and then it goes away because there's nothing to keep it there. Nothing happening, in other words. So let's go ahead and hop into some of our other game capabilities. We're going to do a game loop. Let's go ahead and get that. So we'll do def game loop. That will get a self. All right, and the first thing we want to do inside our game loop is we actually want a while true. We want it to just go on forever unless something breaks out. And then we want to go ahead and start collecting actions. So we want some kind of, the ability to get keystrokes from the user. And as we're building this up, I'm going to start by basically just letting you as a human control both sides. And then we'll eventually move over to having bots control one side and letting you play against the bot. And then after we're done with that, we will set things up so that the AI can start to get into the mix, and we'll get our training loop, and there's a whole bunch of code in for that. But let's go ahead and say player 1 action. So we're going to start them off as 0, and we're going to map 0. So player 2 action, we're going to map 0 to non-movement. So we're basically going to say if nothing happens to change not moving, then we're just going to go ahead and not move. So for event in pygame.event.get, if event type is equal to pygame.quit, then pygame.quit and sys.exit. So basically we want the ability to exit the game and leave if pygame quit's called. So let's try that. Oh, I left out a colon. Okay. Very good. So we created our Pong game. You know what? What I expected to happen is I expected the game to remain open, and it didn't, because while we created a game loop, we did not call our game loop. So let's go over to main.py, and we're going to do env.game loop. Okay, so now what we have is we have a successful game loop, so our Pong screen sticks around. We're no longer, just closing it out instantly. But if I X this out, it should, yep, it's successfully called event quit, and we are now able to keep an open window for our game. And that's why our while true is okay, because closing the window closes the game. Now we need to go ahead and get key presses. So keys is equal to pygame.key.getPressed. So it's going to grab any key that gets pressed here. And we're going to need a little bit of logic here. So we'll say if self.player1 is human, then we want to say if keys pygame.k uppercase k lowercase k. So what that's going to do is grab the key, that's that first k, of lowercase k. So if key k is pressed, then player 1 action is equal to 1. Elif keys pygame dot k underscore j, then player one action is going to be equal to 2. And this is a good place to say you do not have to use the same key combos that I am. These are what I find easy and comfortable while playing. You can totally change these up. I would recommend starting with mine and then tweaking, but you can make changes. So let's go ahead and grab 5. Let's copy those. And we're just going to say if self player 2 is human, then if the key of E is pressed or the key of F is pressed, then player 2 action and player 1 action. Okay, this is a good place to go ahead and we're checking for human because we're also going to throw in bot players and AI players, and there's going to be more here. So let's go ahead and we're just going to get some logging going. Player 1 action is player 1 action. And then copy that. And we're going to say player 2 action is player 2 action. And we'll run it again. So what should happen, oh, that is not what should be happening. So let's see why we're messed up. Well, one, I see I messed up player 2 down here. So what we should see is just a solid page of zeros. So let's just get rid of that. Let's do player 2 action. Okay, we're still getting some 1s. Let's see what's wrong with the logic here. I think I see what I did wrong here. I did not need that that first block around keys. So I think it's just checking to see if there's a value in keys, and that is not what we wanted. I double blocked when I didn't need to. Okay. And then also, just because this output is going to get really annoying, I'm just going to say if player 1 action is not equal to 0 or player 2 action is not equal to 0, then print. So it shouldn't print anything, but if I hit J, then I get 2s because we said J was action 2. If I hit K, I get 1s for player 1. If I, here, even that is a little visually noisy and it's annoying. Let's get rid of that and do if player 2 action is not equal to 0. There we go. Now it should be pretty good. All right. So if I hit J, I get player 1 action 2 down here in the bottom left. If I hit K, I get player 1 action 1. And over on the other side, I picked E and F. So if I hit E, I get, let's see, nothing. And this is why we validate. So why, hang on. We have a logic, we don't have a logic problem. We have logic working as intended. So if I go to our main.py over here, we said that player 1 and player 2 were player 1 was a human and player 2 was a bot. So it is not responding to human commands because it wasn't supposed to. So now, if we press E, we get player 2 action 1. If we press F, we get player 2 action 2. If we press J, we get player 1 action 2. And if we press K, we get player 1, action 1. I'm going to say it is important to pause and make sure all of this works before you go too much further. All right. Let's go ahead and set up our screen background filling, because that's going to be important. We are going to need the ability to fill the background. So right under reset, let's do def fill background self, and we're going to need to add some things to reset to make this work. So we'll do self.screen.fill self.background color. And did I actually add a background color? I certainly hope so. Okay, I have not added a background color. So let's go and do that. We'll put it right under player 1 and player 2 color. So we'll do self.background color is equal to 0, 0, 0. All right, simple enough. We will put, let's go ahead and get a call for our fill background. And we're just going to put that at the very beginning of the game loop. I think I see no reason not to. Not self.background color, self.fill background. Okay, we have a black background, which to be fair is exactly what we expected. And then we're going to need to go ahead and display scores and such for our player. That's probably a good thing to have out there. So let's go ahead in our reset, and reset is going to get called after every episode instead of destroying the game. So we want reset to do things like, zero out the scores. So instead of putting scores up here, we are just going to define them in reset, but not, hang on, down here, that reset. So we're just going to say self.player1 score is equal to 0, and self.player2, if I could spell player, score is equal to 0. We'll do self.top score is equal to 20. So that's the top score that you can get. And then down here in fill background, we will be doing a score rendering. So player 1 score surface is equal to self.font.render. And we'll do score self.player1 score. We will pass in a true. I'll be honest, I don't remember what the true is on this one. Let's bring that down for formatting. And then we'll be passing in self.player1 color. And then we'll do the exact same thing for player 2 score surface. And we will go ahead and do self.screen.blit player 1 score surface, double parentheses, and this is where we're going to place it. I'm going to just do it with a little bit of math instead of trying to make it static. So this one's going to be self dot window width divided by 2 plus 20 for a little bit of padding, and then 10 pixels down. And I should have put that in there. And then we'll do the same thing with self.player2 score surface, except in this case, it's going to be self.window width divided by 2 minus player2 score surface dot get width minus 20. And that's going to let it come over from the left. So let's go ahead and give myself a little more spacing there. Let's see if that's doing what we expect. Okay, that is not happening, and it's probably not happening because I left it out of the while true. I'm guessing that's why. Okay, we still don't have surfaces displayed. Ah, I know what's going on. We do not yet have our, we don't have our step in place, so we don't have our display flip in place, which is okay. We can fix that. So, what we need to do is we actually don't need this in the game loop directly. We could, and if we were not building a game that was intended to be an RL environment, then I would keep a lot more things in the game loop. But what we're going to do here is we are actually going to create a step method, because that's what our agent is going to need later. So let's go ahead and define it. So we're going to do def step self, and step is going to need a player 1 action and a player 2 action. And by default, we're going to set those to none and none. And inside step, we are going to go ahead and call self.fillBackground. And then we're going to say if self.renderMode is human, we're going to go ahead and do self.clock.tick self.fps and pygame.display.flip, which is what we need to actually flip the display and should be displaying our scoreboard. But again, I have to actually call the method. So let's go back to our game loop. And inside our game loop, we're going to call self.step. And because we set those defaults to none, we can just call it. All right. Did you mean Pong object has no attribute clock? Well, why not? Because I said pygame.clock, and which it didn't like at the time. It is trying to alert me that I'm doing something I can't really do. So let's do self.clock. Hey, and there we go. We've got our purple score and we've got our green score. So we now have a background, we have scores. We are in a relatively good spot there. And that's probably a good place. If I'm looking at my counter right, I think this video is about 40 minutes long. That's probably a good place to stop. In the next video, we will go ahead and get into the paddles. We'll start getting into some game dynamics. And then maybe the one after that, we'll start talking about AI. So with that, I will say until next time. Welcome to part 3 of the Dueling AI series. Today we're going to be working on adding some actual gameplay functionality to the Pong game, but a bit of housekeeping first. So if you had any trouble with the last video, something I've always at the end of the videos published the full repository for anyone who had trouble along the way and wants to look at it. What I'm going to do this time is every single time I release a video, I'm going to commit the code from that video to the repository and tag it with the video part. So if you just finished part 2 and the code isn't quite doing what you expected and you'd like to go reference my part 2 code, you can come to GitHub. I'll post the link in the video description, and you can click the part 2 tab or tag, and that is going to take you to the latest code as of part 2 in the video. You can see that's a commit from 10 hours ago. I was working on it last night. So same with this one. If you get to the end of this video and there are things you feel like you've missed, you'll find a part 3 out there at that point, and you can go and look up the code as of the end of the part 3 video. All right, with that out of the way, let's take a look at what functionality we have right now, just as a quick refresher. So where we left things, we have a Pong game, or we have a screen with a score on it. It's not really a game yet. And we had it to the point where you could do J and K and feed in player 1 actions, or E and F on the left hand, and it feeds in player 2 actions. So that was working. And by the way, you do have to have this selected. If you click on your editor and try to hit EF, it's not going to do anything. That's what got me just a minute ago. So we've got that up and running. Let's go to, that split my windows not the way I wanted. Let's try again. All right. We've got our game.py, and the next thing that we're going to do here is go ahead and actually start working on some of our assets, which are actually not going to be in game.py. They're going to be in assets.py. So let's just create an assets.py, and that's going to hold things like our paddle, our ball, and that should be it. We don't have any other game assets. So let's go ahead and we're going to do a few imports. We're going to say from random import. No, that's not what I wanted. From random import random. We're going to import Pygame. We're going to import NumPy as NP. We'll be using NumPy later. And that should be it. Actually, instead of this, let's just do import random. Okay. And then the 2 classes we need are class paddle. We'll throw a pass in there. And then we need class ball. All right, and we're going to implement class paddle first. So the core object that you end up working with most of the time in Pygame is a rect or rectangle. So that rectangle needs an X coordinate, a Y coordinate, a width, and a height. So what we're going to do is we'll do our def init, and we're just going to do X, Y. We'll go ahead and pass in a player color. We need to give it window height, because this will help us figure out where the paddle's supposed to be. And then we'll do width is equal to 20 and height is equal to 120. This is probably a good place too, where if you are using a smaller screen, you want to be looking at what your actual sizing should be. All right, we're going to go ahead and hop down to here and do self.x is equal to x, self.y is equal to y. And actually, let me talk for a moment when I say sizing. When I launch this game, it shows up in a reasonable size for my screen. If you launch it and it's completely off your screen, take a few minutes, go back to game.py and figure out the right game size for your display, whatever that is, the right size in pixels. There are also tricks you can use to do like a virtual screen in Pygame to adjust it without adjusting these. Not going to mess with that right now. That's not really the point of this series, is getting deep into Pygame. But yeah, take a minute now and make sure that this window is the size that you want it to be, because everything else is going to be relative to it. All right. So width 20, height 120. We're going to do self x, y, x, self y, y. And then we'll do self.height is equal to height. Just setting all our params here. And I think somewhere along the line I got, there we go. That's better. Self.width is equal to width. And now we declare our rectangle for the paddle. So self.rect is equal to pygame.rect x, y, self.width, and self.height. Okay. We're also going to declare a speed. Our speed is going to be self.speed is 14. Again, 14 pixels. Self.paddle color is going to be player color. And self.window height is equal to window height. It's another one, since the speed is in pixels. If you go for a smaller size, you need to reduce speed. All right. Next up, we need to set up a draw method for this paddle. So def draw self, and we're going to pass in screen. It'll need a screen to draw on. And then this is going to be pygame.draw.rect screen self.paddle color. And then in parentheses, we're going to do self.rect.x, self.rect.y, self.width, and self.height. Okay. Pretty simple. And obviously you could put this logic outside of the class. For games like this, I prefer to have the move and draw logic where possible inside the asset class itself. All right, now we're going to need def move self direction. And we're just going to throw in an assert here that 0 is less than or equal to direction and less than or equal to 3. Basically making sure that what we're passing in, and actually we don't even need an equal there, we just need less than 3. Basically making sure that anything we're passing in is between 0 and 2. And let's add just a note here. Direction 0 is no action. All right. If direction is 0, we just want to return. We don't want to do anything. Elif direction is 1, then new y is equal to self.y minus self.speed. Elif direction is equal to 2, then new y is equal to self.y minus plus. Here we want to do plus self.speed. Want to go up on the 2's. If 0 is less than or equal to new y, So what we need to do here is we basically just want to make sure that we are inside the world bounds. We don't want our paddle to just sail off into the distance. We want it to, stay on the board. So we're going to say if new y, we're basically saying making sure that it's greater than 0 and that it's less than or equal to the window height. So self.window height minus self.height. So basically we need to subtract the height of the paddle from the window height, and then that's our upper bound. So self.y is equal to new y. And then we set a self.rect.top left is self.x and self.y. All right. And we're not calling draw in here because draw will be called by the external loop. So these two are separate. We will in the main loop we'll call move, and then we'll call draw. All right. And it's complaining about new x and new y. Let's see why. Where should I have had that? All right, I went and took a look, and it was just my editor config. It was complaining about this being potentially unbound, and I really don't care. Another way to solve this would have been to throw it up here as a blank variable or as a 0. But if it's 0, we're returning. We're checking for asserts up here for direction. I'm pretty confident that this code is not going to result in an unbound new y. All right, so we're good there. That is the end of our paddle class. Let's go ahead and go back to the game.py, and we're going to implement our paddle. And give me just a moment to get GamePy pulled up on my other screen. All right, so we're going to set our paddle in the self.reset method. And we're doing it here so that it will get reset to the original position anytime the game resets. We want the paddles to go back to right where they're supposed to be. So player 1, self.player1 paddle is going to be equal, we need to go import paddle from assets, import, we'll just import star. We'll need the other things later. Okay, so paddle, and x is going to be self.window width minus 2 times self.window width divided by 64. Y is equal to self.window height hang on, divided by 2 minus self.paddle height divided by 2. Player color is equal to self.player1 color. And height is going to be self.paddle height, things that we've set statically. Width is equal to self.paddle width. And window height is going to be equal to self.window height. And what this should do is this should put player 1 paddle right in the middle of the left side of the screen. I believe we put player 1 on the left. We're about to find out. This is the downside of writing code and then coming back two and a half months ago or later and talking about it. So let's go ahead and throw an update in our step function that's going to actually display these things, because we're going to need that. All right, so right here, we're going to do self.player1 paddle.move, and it'll be whatever player one's action is. And then we will do, we actually need self.fill background down here. So we're going to move player one's paddle. We're going to fill the background. And then we're going to say self.player1 paddle.draw. And we'll pass in screen is equal to self.screen. Okay, let's see what happens. Hey, we get a crash. Okay, not supported between instances of int and none type. Okay, that's all right. We're just going to default to 0. Later on in the code base, we have enough set up to make sure this is always valid. All right, we have our paddle here, but it's not doing anything. We're not getting any movement. And I don't think we're getting any movement because when we call step, we are not passing it anything. So let's go ahead and come up here to down here to our game loop. And in our game loop, we need to call player one action is equal to player one action, and player two action is equal to player two action. And now you should be able to hit J and K and have a little moving paddle. So we have the start of some functional game mechanics, which is a really cool place to be. All right, let's go ahead and close that out. And we're going to go and set up the other paddle. So we can basically just copy all this and come down and paste it. And we're going to make it player two paddle. And then we just need to make a few small edits here. So it's still going to be, instead of self.window-width -2, so this is the part that basically pushes it over to the right. So self-window-width -2 is basically saying, hey, we're gonna shove you all the way over to the right-hand side of the screen. We don't need that anymore. So now we can just do self window width divided by 64. That's going to give us the appropriate level of distance from the side of the screen. And then we can do self window height divided by 2 minus self dot paddle height. And that's still going to place us right in the middle. And then we'll do player 2 color. And then everything else here should be able to stay the same. Now let's go back down to our step method. And we're just going to copy this and have player 2 paddle move with player 2 action. And we'll copy this and have player 2 paddle.draw. And at this point, we should be able to run the code. And we now have 2 paddles. And you can control one of them with E and F and the other with J and K, which is a really cool place to be. So now we have most of our game. We've got some paddles we can control. Let's go ahead and implement a ball. All right, so this is going to be back in assets.py. if we come down to our class ball, we're going to do something very similar. So def init self dot, well, not self yet, window height, window width, player 1 paddle, player 2 paddle, and then our ball width is going to be 10, and height is going to be 10. All right, and that's exactly what we expect. So as usual, we're going to go through and do self.height is equal to height, self.width is equal to width, self.window height is equal to window height, self.window width is equal to window width, self.player 1 paddle. So this was something that I struggled with on the decision making side, where to actually put the collision detection, and where I landed was putting it in the ball. So basically, we're going to pass player 1 and player 2 paddles into the ball move method, and we'll do collision detection in the ball's move method to see if it has if it's hit one of the paddles. That's the way we're going to handle this. So player 1 paddle is equal to player 1 paddle, self.player 2 paddle is equal to player 2 paddle, self.ball color will be 255, 255, 255. And self.max speed is going to be equal to 30. All right. And we're going to need this later, but let's do self.last serve left is equal to random.choice true, false. All right, this is probably the first place where we're going to talk about something that's actually RL related. So one of the things that I noticed really early on was doing self-play was seeing consistently higher scores for one side than I did the other. And it actually really threw off training. And there was a lot that went into that. But one of the big smoking gun issues was that it always served to one side. So I had it by default, hadn't thought about it. It just always fired off to the right, which meant that the player on the right was being constantly peppered with, shots from the ball, and the player on the left only got served a ball when the player on the right actually hit it. So what we're going to be doing is randomizing the direction that the ball comes from. That's another thing that maybe wouldn't matter. It would matter for fairness if you were playing against a computerized component, but it wouldn't really matter for learning. If the agent was always served the ball, it doesn't care. It's going to learn how to hit the ball. If the ball goes in the other direction all the time, if it's always not served the ball, then it'll just learn how to respond to another player hitting the ball at it. But if you are doing self-play, then having, one side of your agent constantly served a ball and the other side not is a little bit of an issue. All right. And then finally, we're going to call self.spawn. And we don't have a spawn method yet, but we're going to create one. So let's go ahead and do def spawn, pass in self. All right, so self.x is equal to self.window width divided by 2, and self.y is equal to self.window height divided by 2. So we're going to drop the ball right in the middle of the screen. Speed is going to be random.choice from 10, 12, and 14 pixels. and that's how much it's going to move every step. And the reason I made it random is frankly just to make the game more fun. You can have one static speed. I find that firing it off at various random speeds to make it a little more interesting. All right. And then self.lastServeLeft equals not self.lastServeLeft. This is basically going to flip last serve left every single spawn. And then self.vx, so this is going to be our x velocity, is equal to the negative of speed if self.lastServeLeft else speed. All right, and what we're basically doing here is we're saying our x velocity is going to flip every time. That's what these two lines give us. In fact, let's add a comment. Flip x velocity every spawn. So every time we spawn, we flip. Self.vy will be a random.choice between -6, -4, -2, 2, 4, 6. So basically, this is going to make it fire off at various angles throughout the game. And we could have done something like this, random.choice, for just direction or, X speed. We could have done, negative 14, -12, -10, and that would probably work fine. The reason I'm hard coding this a little bit better is, or a little bit more consistently, is during training, I was trying to I was running into problems with things that were throwing the balance off, and I was trying to just be really, really consistent with how often I served each side of the ball. You could do just a straight random.choice like this with negatives included, and it would probably be fine. But the implementation above is just a little bit more robust. All right, so we're going to do self.rect. Again, everything's a rectangle. Pygame.rect, self.x, self.y, self.width, and self.height. All right, we now have our ball spawn. The next thing we're going to, this will be a little helper method. So get step increment is, in fact, let me see if I actually used that helper method. Yes, I did. All right. So def get step increment self velocity. If vel is greater than 0, return 1, else return -1. All right. This will make sense in a minute. So our next and final method here is our move method. And this is going to be a little bit, we need move and we need draw. So let's go ahead and work on, let's do draw first. Draw is going to be super easy. So def draw. And actually, you know what? If you have been following along, pause and go implement your own draw method based on what you saw in the paddle. All right, I'm going to continue. For those of you who tried, hopefully it worked for you. So self screen, pygame.draw.rect, screen, self.ballColor, self.rect.x, self.rect.y, self.width, and self.height. All right, we now have our draw method. And I'll give myself another space there. All right. Next, we are going to define our move. And this one is going to be kind of complex because it includes collision detection. So we're going to do def move self. And then just like we've done in other places, we're going to do new x is equal to self.x, new y is equal to self.y. And we're basically just going to be editing those new y variables as we go. And then at the end, we will, set self x and self y to them. So we'll do x step is equal to self.getStepIncrement, self.vx, and y step is equal to self.getStepIncrement, self.vy. And let's talk about something we're going to be doing here in y. And this is going to be hard to visualize, but you can do a simple implementation of movement in Pygame is just to add speed, whatever the speed variable is, to your moving object every single step. So, and it actually looks fine visually most of the time, because if you're moving by 10 pixels, it's basically just going to, inch along at 10 pixels, whatever that, whatever that increment is until it hits the paddle. The problem is when you get into collision detection and scoring detection, you need to know the exact pixel when something came into contact. You can't have your ball go 5 pixels into the paddle. And that's especially important when you get to scoring. If a score is when the ball is completely off the screen versus a score is when the ball just touched. You also get into some weird stuff where, like, if you're checking for collision, but you only check midway into the paddle, the ball can get stuck and just like stick to the paddle because you've, tried to reverse direction. There's lots of bad stuff that can happen if you are not fine-grained enough with your collision detection. So what we're doing here with these X step and Y step is, even if velocity is that we are going to move by 10 pixels or 14 pixels or wherever we land at, we want to take that in single increments of 1 pixel. And those single increments need to be in the right direction. So that's why we have this getStepIncrement function to go ahead and say, hey, if velocity is positive, then I want a 1. I want 1 to be my step increment. If velocity is negative, then I want -1 to be my step increment. And then we're going to iterate towards whatever the final position was supposed to be. And if we hit a collision anywhere along the line, we're going to stop and report that collision. All right. We are going to do new rect is equal to none. We're not going to declare one yet. We are going to do, let me check something real quick. All right. We're going to need an early collision detected. And we're going to set that to false in the beginning. And then we'll do if self.rect.collide rect self.player1 paddle, or self.rect.collide rect self.player2 paddle. That's getting a bit long. Let me just drop that down. Let's see. Then early collision detected equals true. And what we're doing here is we're trying to figure out if it's already collided, because again, we want to avoid that stuck to the paddle problem. This is something I did a lot of troubleshooting on, where I'd be playing, and then if it hit the paddle the wrong way, it would stick to the paddle and then sit there cycling with the ball stuck, which is really not ideal. So here we're going to do for I in range, and we want the absolute value in integer of self.vy. New y is equal to new y plus y step. So again, this is us taking small steps. If not, early collision detected. And then in our inner if here, we're going to say if not 0 is less than or equal to new y is less than or equal to self.windowHeight minus self.height. So again, we're basically just saying if it's not already collided and it's not inside the, if it's not out of the world bounds, then we want to say self.vy is equal to np.clip, because we want to stay inside of a maximum speed. Self.vy times -1. Let's see. Plus self.random choice. Not self.random choice. Random.choice. -1, 1. And we want to clip that to the negative of self.max speed and self.max speed. And then we want to break. So let's talk about what we just did, because that was a whole bunch of numbers here. So what we're basically saying, so no early collision was detected, but then we're saying if not inside the world. So what inside of the world from a y perspective. So remember, y is up and down. So this is saying if you collided with the top or the bottom of the window, then we're going to set y velocity to -1, and we're going to add, randomly add either -1 or +1. So we're going to add a little bit of randomness to that bounce. And when I say to that bounce, let's show what that would look like a little bit. So what this logic implements is if the ball is headed up, so, you know, in this scenario, our y velocity is, let's say 5. So we're heading up, we've got a 5 y velocity, we hit the top. Well, we now need a -5 velocity. So we just applied a negative and then it bounces back down. We don't need to change x. X is still moving to the right here. We just need to change y. So we hit top, we bounce back down, we keep going. Again, with a little bit of randomness, just to mimic what would really happen. Again, if you think about it like, you know, you're playing pool, you hit a ball, it hits the side of that pool table, it's not bouncing perfectly. It's going to randomly, or at least randomly as far as you can tell, wobble just a little bit. It's going to move a little more than it would if this was a perfect, you know, equation. So that's what we're trying to model here, is a tiny bit of randomness in the process. So next up, we are going to come down here and say, actually, let me get a little bit of extra room there. I think that helps. Actually, no, it doesn't. It makes it harder for me to see. I'm blowing the text up drastically to make this visible for YouTube. It is clownishly large on my screen though. So let's go ahead and say if, actually no, we need to go ahead and do new rect is equal to pygame.rect. So now that we know we're not colliding with the top or the bottom, we can go ahead and do pygame.rect newx new y, and self.width, and self.height. And then if new rect dot collide rect self.player1 paddle, or new rect dot collide rect self.player2 paddle. All right, I'm going to do another, bringing this down. Then we're going to grab self.vy is np.clip self.vy plus random.choice again, -1, 1, and self.max speed, and we want the negative of self.max speed, and self.max speed, and then break. Okay, so now we just handled some of the paddle collision, so for range. So basically we're slowly iterating here on the y dimension, and that is a point to remember. So everything we just did here was a for loop around the y collision. So now we're going to go and work on the x collision. So for I in range, ABS int self.vx new x is equal to new x plus x step. If not early collision detected, then new rect is equal to pygame dot rect new x new y self.width self.height. Okay. And we don't have to do a whole bunch of logic for early collision because we already did that. So now we can say if new rect dot collide rect self.player1 paddle, or new rect dot collide rect self.player2 paddle. We'll do another. You know what? I would rather have that line up. Then we want to do self.vx is equal to np.clip self.vx plus x step times -1. And we want that to be negative inside self.max speed and self.max speed. And what we're doing here is we are both invert the ball direction and speed up the ball slightly. So that's actually going to, the gameplay dynamics that we're trying to get here are if the paddle hits the ball, if the ball hits the paddle while it's going in an X direction, it should actually speed the ball up a little bit. And that's another making the game more interesting kind of thing. At some point, the ball will, if it continues to move at its original relatively slow speed, it becomes an uninteresting game. You hit the point where it's going to score, it's going to hit the ball perfectly every single time. It's going to bounce back and forth. By adding a speed up component, what we're basically landing at is as the game goes on, the ball is going to get increasingly faster, and then eventually, hopefully, one side will score, whoever misses it first. So this is to model those dynamics. So we want to say self.vy is equal to np.clip and then self.vy plus random.choice, -1, 1, and then again, we want to clip that inside self.maxSpeed and negative self.maxSpeed and self.maxSpeed, and then we want to break because we've collided. All right, and then now that we're done with our for loops here, if we've made it down here, we should be in a place where self.x can be new x, self.y can be new y, and self.rect can now be pygame.rect new x, new y, self.width, self.height. Okay. Assuming no typos, this should now be complete. So let's go back to our game.py and implement. All right, and I'm taking a moment to remember where I put that code. All right, this is going to be in reset. So we're going to go to self, we're going to declare a self.ball is equal to ball. And then we'll pass in window height as self.windowHeight, window width as self.windowWidth. Height in this case will be 20. Width is equal to 20. And we'll pass in player1paddle equals self.player1paddle. And player2paddle is equal to self.player2paddle. Okay. Now, if we get down into our step method, this is where we've played out our, we've done our player1paddle move, fill background, player2paddle, draw. Now we need to do self.ball.move and self.ball.draw. Screen is equal to self.screen. Okay. Let's see if we've missed anything. Okay, we now have a ball. But as we can see, it flew off the end of the screen there and is no more. So let's close this out. And we actually need to make a couple, let's go ahead and make a structural change that's going to come in later. So one of the things that we're going to need to do is be able to repeat an action. So something, if you pass in an action of 1, you want it to repeat a certain number of times. And that's mostly, it's perfectly fine to not do that on a human playable game. But when we get to the AI playable section, you want your AI to get somewhat notably different observations each time. You don't want a replay buffer that's completely full of things that look identical because only one pixel has had time to change between frames. So adding an action repeat and allowing it to say, hey, move up, and then have it move up 3 or 4, cycles. Again, keeping in mind, we're talking about a few frames of movement, not shooting the paddle all the way up to the top, just giving it something closer to a human, reaction speed requirement. That frame step is going, or frame skip is what that's normally called. The way we're going to implement that is we're going to say underscore step. So we're going to change our step method to an underscore step method. And that's basically going to make this an internal method. And then we're going to do our external step method, which will also have self player 1 action, player 2 action equals 0. And then what this external step is going to do is it's going to say for I in range, self.step repeat, self.step player 1 action equals player 1 action, and player 2 action equals player 2 action. All right, before we try to fix anything else with the ball, let's just go ahead and make sure that the game still works. And it does. Okay, we now have our step repeat is functional and working. So the reason I went ahead and fixed this is we are going to add the ball spawn capability to this outer step method. So here we're going to say that ball center, and this is important, we want to count a score only when the ball center is over, not when the ball left, because by default the X and Y are, if I recall correctly, the top left-hand side of the object, the ball. So we want to make sure that only when the ball center crosses off the screen do we count a score. And the reason we want to do that is because if you don't, you end up with a case where the ball is completely gone off the screen on the right, or isn't gone at all off the left, and the score is still counted. And that gives your agent a very inconsistent goal. This is something that is, as you're designing games that are meant to be played by AIs, you know, a human can look at the whole game and understand, like, we don't even notice the difference between scoring when the ball is, you know, 90% over the finish line versus when it's just touched the finish line. Like, we understand intuitively that the ball made it, we scored. You know, you don't have to tell a person that that's what happened. And in fact, because these things are moving fast, we don't even notice. Your AI is literally looking at the frame that a reward was returned on. So if that frame shows that the ball is still in the picture, that is a very different view than showing that there's no ball on the screen. It's not going to understand that no ball on the screen means it just scored. So the logic you use here is important. So self.ball.x plus self.ball.width divided by 2. All right, so we're going to say if ball center is less than 0, then self.player1 score plus equals 1 player 1 reward. And in fact, let's go ahead and declare these up here. So we're going to do player 1 reward is equal to 0. Player 2 reward is equal to 0. And then we'll need these later. So let's just go ahead and do done is false. Info will be an empty dictionary, and truncated is false. All right, there we go. So we want player 1 reward plus equals 1. Player 2 reward minus equals 1, because if player 1 scored, that means player 2 failed. And we want self.ball.spawn. And then down here, we want to say elif ball center is greater than self.window_width. Self.player2 score will be plus equals 1. And player2 reward will be minus equals 1. And player1 reward will be, actually, no, hang on. Player1 reward will be minus equals 1. And player2 reward will be plus equals 1. And then we will again self.ball.spawn. Okay. Okay, so you'll notice, and by the way, if it's not obvious, this is me playing both sides. So at this point, you are 100% human controlled. And what you'll notice is that every time it goes over, we now get a successful score method. So we're basically at a point where a human can successfully play either side of the game, which is a really good spot to be. Now, we don't have any kind of, end game logic in here. The way this is set up right now, I'm just going to park that off to the side. It'll basically sit here and score forever. There's nothing stopping it from just continuing to rack up points, and the game will never end. There are also no computerized opponents, so nothing for us to play against. And obviously, we're not at a point where we can quite link this in and start doing reinforcement learning on it. So this has been, I think we're at 57 minutes of video. So I'm going to go ahead and end this one here. In the next video, we will go ahead and start working on an end game system so that it doesn't just sit here and play forever. And we will build out our bot players that we'll later use as a scoring mechanism to see how well our AI is doing. So with that, I'll see you in the next video. Welcome to part 4 of the Dueling AI series, where we're working on a self-play architecture with a custom Pong engine. Where we left off in the last video is we have our Pong game mostly playable, but it's me as a human currently controlling both paddles with my keyboard, which is a fun little challenge, but not really what we're trying to do here. So in this video, we're going to go ahead and implement a bot player. So this will be a statically coded bot that later on we can use to score the AI. If you're training an agent against itself, you need some ability to have a yardstick to measure its performance against. So in this video, we're going to go ahead and work on that yardstick, work on that bot player. And we're also going to implement the game over dynamics and a little bit of some of the reward capabilities. So we're going to be trying to really round out the game in this video so that we can hopefully in the next video go ahead and start working on some of that agent functionality. So let's go ahead and start with a getBotMove function. So getBotMove is going to be part of the Pong game function. And it's going to be getBotMove self, and we'll pass in player. And we want some degree of randomness. So it's actually pretty easy to code a bot that is really, really difficult to play against. You just make it track the ball. But you want some randomness so that when you're, playing against your perfect ball tracking bot, it needs to occasionally make a bad move, or it's really, really hard to score against it. Other games are probably a lot harder to make a perfect AI player or a perfect bot player, but this one, pretty easy. So we want a little bit of randomness. So our random target is going to be 0.1. We're going to set next move to 0. We are going to grab the player Y. So existing player Y is self.player1 paddle.y if player is 1, else self.player2 paddle.y. All right, and then we're going to have different bot difficulties. So we're going to start with if self.bot difficulty equals easy. We're going to say if random.random is less than or equal to random target. Then next move is random.rand int 0, 2. So just a random number between 0 and 2. Else, if self.ball.vy is greater than 0, next move equals 2. Else, next move equals 1. It'd help if I actually put this down. And then finally, at the end here, return next move. All right. So what this logic's going to do is it's going to track the direction of the ball, and it's going to move the paddle in that direction. What you'll notice, and the reason this is the easy bot, is it's not actually taking any account of where the ball is in relation to the paddle. So it doesn't know if the paddle's already higher than the ball. It just knows ball goes up, paddle goes up. So it's playing like a very reactive player, like somebody who is just like, oh, I see the ball bouncing towards the top, I'm going to shoot the paddle to the top. That's basically what our easy difficulty bot is going to do. So let's go ahead and implement our get bot move. And we're going to implement it in a couple of ways and places. And the reason you're going to see some duplication here, and some of why you're seeing duplication, is that we are going to run into some issues, or not issues. We're going to be using the game loop when we as humans are playing the game. But we're not going to be using the game loop when the AI is training on the game. The game loop is purely for the human playing. So we're going to need some safeties in step, as well as some intentional logic in the game loop itself. So let's start by going down to step. So here's our step method. And what we're going to do here is we're going to say if player one action is, and this is where we actually need to change this from 0 to none. So we're going to say if player one action is none, then player one action is equal to self.get bot move with a player one. If player two, and I'm intentionally not using an elif because we could have either or both not have a move. If player two action is none, then player one action or player two action is equal to self.get bot move 2. All right, so that's a safety. That's just there to catch things that we weren't expecting. Let's go ahead and head up to our game loop. Okay, so right around here, where we're checking to see if players are human, we want to go ahead and first off, we can go ahead and delete these. We don't need these prints anymore. They are not necessary. So we need to say if self.player1 is equal to bot, then player1 action is self.getBotMove player equals 1. If self.player2, actually, let's just copy. So if self.player2 is equal to bot, not player22, player2, then player2 action is going to be self.botMove player2. All right, so at this point, what we should be able to do is go over to our main.py, and I am just going to comment out that first one. We'll make switching back and forth between them a little bit easier. So I'm going to say player 1 is human, player 2 is bot, and bot difficulty is easy. All right, so at this point, I am playing the green paddle, and my easy bot is playing the purple paddle. And you can see it really is an easy bot. It kind of moves in the general direction that the ball is moving. And sometimes that's okay. You can see it just caught one. But it's not the best logic. It is exactly what you would expect from an easy bot. So what I'm going to recommend is this is a great time to pause the video and challenge yourself a little bit. So we just created an easy bot in game.py. I am going to challenge you to go and build yourself a hard bot or do an intermediate bot. If you'd rather watch me build the hard bot and then you do like a medium bot, that's fine too. But I'm going to say pause now, go build yourself a hard bot, and then come back to the video and see how I do it when you're done. All right, I'm going to assume that the people who wanted to pause have done so and have built their hard bot. Let's go ahead and build our own hard bot. All right, we're going to do elif self.bot difficulty is equal to hard. So we're still going to do our random target logic. So we still want a tiny bit of randomness. We want about 10% randomness. Else, if self.ball.y is greater than player y plus 60, that's for 60 pixels. Next move equals 2. Elif self.ball.y less than player. All right, less than player y plus 60. Then next move is equal to 1. And this is pretty simple logic, but basically what it's going to do is track the ball perfectly, except for that 10% of the time. And it will look a little bit erratic, but it'll also play very, very well. So let's go ahead and come back over to our main.py, and I'm going to do another copy paste. And this time I'm going to say bot difficulty hard. Oh, that did not. There's definitely something broken. I have a typo somewhere. Hang on. Let's go over to our game.py and figure out what I messed up. So Difficulty, random target. Yep. Next move, random target's pretty low. Here, this is supposed to be a greater than. I had both less thans, which was not what was intentional. All right. Again, you can see a little jittery, but my hard bot hits basically every time. It is really hard to score against it because it's tracking. And it does occasionally mess up. You can get a score in sometimes during that 10% randomness, but it's hard to do. So we've successfully written a static hard bot that is capable of beating me pretty easily, especially when I'm distracted and trying to talk and play. But I will not win against the hard bot in general, which makes it a really good yardstick to train our AI against. So let me pull up our training graphs here. Give me a moment. All right, so I showed these training graphs in the first video. And what I did here is I played the first 350 episodes against the easy bot because, after that point, the agent just wins all the time and it doesn't really give us anything interesting. It's just time. And then I started playing against the hard bot, which you can see we never really get a score of above about 3. But now that you've seen the hard bot and you see that it's pretty accurate, it's going to track the ball. So let's talk about its accuracy level for a moment and what a score of 3 means in this context. 3 to 4, an average score of 3. So the hard bot, if we're doing something random 10% of the time and we're tracking the ball perfectly 90% of the time, you also have to assume that out of that 10%, about half are going to be the right move in any given time. So let's say that we're 95% making the right moves with the hard bot. We are only playing 2,000 steps in our training runs here. So what that's basically saying is that inside of 2,000 steps, we are able to score, 3 to 4 against a bot that only ever misses or only does the wrong thing, not necessarily misses, 5% of the time. So the scores that we're going to get later in the course, later in the video series, against that hard bot are actually incredibly good. It may not look like a lot. Again, hitting 3, it's not super satisfying. It's not like watching it hit 20. But it is a really good response from what we're going to have here. All right, let's go ahead and we need some game over logic because so far we can basically just play forever, which is less than ideal. So we're going to go ahead and do a game over down here. So def game over self, and we're going to say if self.player1 score is greater than or equal to self.top score, then we're going to create a game over surface that's self.announcement font.render player1 true. Still don't remember what that true is. And self.player1 color. And actually, we'll just wait. And then I'm going to copy this whole thing and do the same thing with player2 score. self.player21, self.player2color. All right. And then we will do a game over rect is equal to game over surface dot get rect center equals self.window width divided by 2 and self.window height divided by 2. And we're doing the double slash to get an int out of that, if I recall correctly. It's been a little while since I've touched that. And I realized looking at this that I have one of the parentheses in the wrong place. There we go. That's what we want. We're going to do self.screen.blit, game over surface, game over rect, pygame.display.flip, self.done will be true, time.sleep 10, just to give you time to see the message. And then we'll do pygame.quit and sys.exit. All right. And we need to go to the top and import time. All right. We've successfully imported time. We've got our game over screen. Let's go down to our step function. Let me get rid of that. All right, so we're in our step function here. We are going to say that if, we need a couple of checks here. So if self.player1score is greater than or equal to self.topscore, or self.player2score is greater than or equal to self.topscore. And by the way, if it feels like we're duplicating logic, we are a little bit. And it is, again, because there's more than just human players. So we need a couple of checks. That'll be a little bit of a theme here. So we're going to say if self.renderMode is human, then self.gameover. Else, we're just going to set done to true and truncated to true. All right. And just for speed here, we're going to set top score to 10. We'll come back and change that later, but I just want to be able to test this real quick. So I'm just going to not fight back against the agent. I'm going to let it score 10 quickly. All right, so we get a player 2-1. This is a good place to go ahead to, and it's going to pause for 10 seconds, and then it should close. All right, cool. That's what we expect. Let's also go and test out let's test player 1 as a bot and player 2 as a human. So this is where I'm going to take over as the purple paddle, and our bot is going to take over as the green paddle. And it's worth mentioning, like, take the time now to make sure all of this works really well. Play as both players as a human, play as both players as a bot, like make sure that it's all very, very functional. Otherwise, what you're going to run into problems later on. You don't want to be troubleshooting the game when what you're trying to fix is your AI agent. You would rather just be able to focus on your agent. So if you see any weird behavior while you're in this phase, now is the time to stop and go fix it. And as a reminder, the GitHub links for each section of the video series are in the video description. So if you hit a point where you've got a bug, you haven't been able to solve it, take some time, go look at the code base, hop on the Discord, ask ChatGPT, whatever your preferred troubleshooting method is, and try to get things working really, really smoothly up to this point. All right, we are now going to go ahead and work on our observations. So this is the first point where we're really going from something that is a game to something that is intended to be a reinforcement learning environment. So we're going to go ahead up under reset, and we're going to do a def get obs, and this is going to pull an image observation from our environment. So we're going to be training on images. We're going to pull back an 84 by 84 grayscale image from the environment for the AI to learn to play with. So screen array is going to be pygame.surf array.pixels3d self.screen, and screen array is going to be where we need to change the dimensions a little bit, or not dimensions, the channels. np.transpose screen array, and then we're going to do 1 0 2. We're going to resize to 84 by 84. So we're going to say downscaled image is equal to CV2. And we do not have CV2 yet. We have not yet imported it. So let's just go to the top and import CV2. We'll also go ahead and import numpy as np and import torch, because those are all things that we will likely need as we're getting into our get obs. All right, downscaled image, CV2, dot resize, screen array, 84 by 84, interpolation, and we're going to do CV2 dot inner nearest. So at that point, we should have an 84 by 84 image. Then we're going to do grayscale is CV2 dot CBT color, downscaled image, CV2 dot color, RGB to gray. And then finally, instead of just straight grayscale, we are actually, and this is another, so let's talk strategy for a moment. When we get into self-play, there are a few different ways that you can handle this. You can handle self-play in an environment by trying to do some kind of player channel to tell an agent what side it's playing on. You can also, for games like Pong, just flip the observations. So you can flip your observation during action selection so that, the agent always thinks it's playing on the same side. So if you think about it, it's a symmetric board. If we train the agent to be on the right side, then when it's playing on the left side, we just flip the observation and it always thinks it's on the right side. The one thing that throws, or one of the things that can throw that off, is that our paddles are different colors. And even when even when you do a grayscale, like the grayscale of purple is still different than the grayscale of green, and it can throw training off and make it more complicated. So what we're going to do is we're going to say grayscale, where grayscale is not equal to 0, set it to 255. So we're basically going to force this thing to only have black and white as its colors. We're doing color RGB to gray. That gets us from 3 channels down to 1 channel of grayscale, and then we're taking that everything is either a 0 or a 255, and giving the agent a very simple black and white image to learn from. So we'll see the game in color. It'll see it in solid black and white. Finally, we're going to do observation is equal to torch dot from numpy grayscale dot float dot unsqueeze to add a dimension we need there. And then we're going to return observation. So now we have a successful get obs. We're really, really close to just being able to, start to work on some AI here. We need to go ahead inside of our step method, and let's go find step. All right, so down inside of our step method, towards the end, actually, let's see, where do we want to put this? We want, right after our step repeat, we want to go ahead and do observation equals self dot get obs. Okay. And you might wonder why we're not putting it in the downstream step method. The reason we're not is because if you put it in downstream step, then it's going to run 4 times instead of 1. It'll run for every single repeat, and that's just extra computation that we don't want to have to do. It makes the game take longer, and when you're running thousands of episodes, making the game take longer is a problem. So we're going to return observation, player 1 reward, player 2 reward, done, truncated, info. And in most gym environments, if you're used to working with gym, you know that you just return a reward. In this case, because we're doing self-play, we actually need both. We need all of it. We're going to grab this line and run up here to our game loop. And I really just want to make sure. Yeah, I don't need that return. I really just want to make sure that if I set these things equal to self.step, let's go ahead and print out observation. I just want to make sure that we're getting what we expect to get. Yep, that looks pretty good. That looks like about what we would anticipate. Let's go ahead, and I don't see any 255s. Let's just go ahead and grab the 0th element of observation. Maybe a dot sum. I want to make sure. That we're okay. Cool. Yes, we are getting non-zero numbers inside of that observation. I'm going to encourage you to go and run the same tests. Let's make sure that player 1 reward, the reward dynamics work. Yep, we occasionally see a 1 and a -1. Player 1's over here on the right. Let's go ahead and do print player 1 reward. And then we also want to do the same with player 2 reward. Okay. And we can go ahead and print out done. Okay, all of these things matter. Okay, so we can see that player 1 gets a +1 while player 2 gets a -1. And if we want to grab our main.py here and just change bot difficulty to easy, because that's going to give me a better, in fact, let's even just do if reward player 1 reward is not equal to 0. That'll clean up some of the visual noise. Okay, so for that one, player 1 scored, and yep, and we're seeing things correctly reverse, and all of our rewards are coming back successfully. So what that tells us is at this point in the series, we have a successful Pong game that can be treated like a gym environment. It's going to return rewards, duns. It is going to allow our agent to play, hopefully, and train successfully. So in the next video, we are going to go ahead and start working on the agent that will start to learn, via reinforcement learning with a basic Q-learning approach, how to play the game. Reminder, again, the code for this video will be in a GitHub tag in the video description. If you run into any issues, you can go check out the tag or join the Discord. And with that, I will see you in the next video. Hello and welcome to part 5 of our Dueling AI self-play series. So today we're going to be working on the model.py, and we're going to start mocking out the agent class. So let's go ahead and just add an agent.py. And then we're also going to add a model.py. We're going to end up using both of them. And we'll start with, we'll go ahead and start with the model, and then we'll be calling the model from the agent a little bit later. So in our model.py, we're going to start out with our imports. So we'll do import torch, import torch.nn as nn, import torch.nn.functional as f, and then we should be at a place where we can go ahead and start our model class. So let's do class model, and that is going to inherit from nn.module. And I'm making some assumptions that you've worked with neural networks before, so I'm not going to go into a ton of depth here. This is a little bit more of an advanced series. If this is all new, there are some other videos out there that are going to dive into this deeper. But let's go ahead, and we're going to do our init. And our parameters here are going to be action dim for action dimensions, hidden dim, and we'll default that to 256. Observation shape will be none. And then we're going to do OBS stack. So in this scenario, we want to be able to show movement over time to the model. So we're actually going to stack our observations, and we're going to default that to 4. In here in super, we're just going to call it with model and self, and then we can get rid of these. Okay. What we're going to need here is 3 convolutional layers. So, and actually this is probably a good place, if you're familiar with neural networks, to take a moment and try to run through this yourself. So we're going to get 3 convolutional layers. They're going to have an input of OBS stack, followed by out channels 32, kernel size 8, and stride of 4. And then the next layer is going to be 32, 64. Kernel will be 4, and then stride will be 2. And then the next layer is going to be 64, 64, kernel size 3, stride equals 1. So if you're comfortable with neural networks, pause the video here, go ahead and code out those 3 layers, code out a single fully connected layer and an output layer that maps to the action dimensions. And then if you're feeling really adventurous, go ahead and give a forward method a shot. And pause now. All right, I'm going to make the assumption that the folks who wanted to give that a shot have done so. So let's go ahead and code this out. So we're going to do self.conv1 equals nn.conv2d. In channels is OBS stack. Out channels is going to be 32. Kernel size 8. Stride is 4. And we'll just copy those over. And we're going to do a conv2 with in channels 32, out channels 64. And you should always see the next layer's input channels will match the previous layer's output channels because we're passing this from layer to layer. And you can think of convolutional layers as sort of walking across the image and pulling out details and then creating an increasingly smaller image with more depth of information as it goes through. That's probably a bad description, but it'll do for what we're doing. You're squeezing it through the convolutional network. We're going to do in channel 64, out channel 64, kernel size 3, and stride is 1. And then we can't forget to call this convolutional layer 3. For our output size, I like to be able to test different things out. So we're going to put together a quick method to calculate the output of our convolutional layers. So we're basically just going to do def calculate conv output self observation shape, and then x equals torch.zeros. So we're going to create a fake input in the observation shape, and we're going to do x equals f.relu self.conv1 and pass in x, and then just copy and paste that for conv2 and 3. And then we're going to return x.view -1 .shape 0. All right. And what that's going to let us do is instead of statically setting the size of the next layer, we're just going to be able to say conv output size is equal to self.calculate conv output observation shape. And then we can do self.fc1, so that'll be our fully connected layer, is nn.linear conv output size, hidden dim, and self.output is equal to nn.linear, hidden dim, and action dim. And then we will also set up a weights init. We're going to, that's going to start things off with hopefully non-biased weights. So def weights init self m, and we're going to say if is instance of m nn conv dot conv2d. then nn.init, and we're going to use chiming normal, m.weight, non-linearity equals ReLU, and we'll do if m.bias is not none, then nn.init.constant m.bias and 0. Okay, and then we're going to copy all of this and say elif is instance nn.linear. And here we will use Xavier normal. And we will not be using a non-linearity here. And everything else should be the same. That all looks good. Okay. So now, back up in our init method, we can do a self.apply and self.waitsinit. Don't accidentally put parentheses after waitsinit. Your editor might try to fill it in. Make sure to pull those out or that will cause problems. All right, finally, we can go ahead and build our forward method. Oh, and something I did want to talk about. So you'll notice we only have one fully connected layer. That is intentional. You can obviously add additional layers. In my experience with this particular problem, more layers does not equal better. It actually makes it take much longer to converge and makes the whole process a lot more complicated. You only need a single layer to solve Pong. Adding any more just adds complication that you do not need. All right. For our forward method, we're going to do def forward, self and x. And the first thing we're going to do is divide x by 255. And I want to explain this one, and it's going to be a little bit more clear as we get into the rest of the setup here. We're going to be saving images in integer values between 0 and 255. That's going to be our standard. We could normalize those in the replay buffer, but then that's going to, and normalizing meaning, of course, to shrink them to values between 0 and 1, which is basically what this is going to do. Dividing a number that's between 0 and 255 by 255 will ensure that all of our results here are, 0, 0.1, 0.2, something like that. So why don't we just store them as normalized values? Well, in this scenario, that is going to, storing them as a normalized value is going to require us to store them as floats. And that will take a replay buffer that's already going to be quite large. This could be 10, 12 gigs, depending on your size and how many images you choose to store. So that can take an already quite large replay buffer and turn it into something that is, hundreds of gigs, depending on how many images you are attempting to store there. Because keep in mind, we're stacking observations. So if we even store 100,000 images, which is a very small replay buffer, we're stacking 4 of them for each image stored. So we're really storing 400,000 images. And even though we are going to shrink them down to 84 by 84, we still need to store them in the most efficient way. So waiting until we get into the forward method to do that normalization allows us to store those as ints, and an int is the most efficient data type in this scenario. All right, so enough on that. We can come up here and copy those lines because it's the exact same thing. And then we can do x equals x dot view, x dot size, 0. And that's going to flatten things out for us. And then we can do x equals f dot relu, self dot fc1, and x, and then output equals self dot output, x, and then we're just going to return output. All right. So that should be everything this model needs from a basic functionality perspective. Something I like to have is I would prefer to have the ability to load and save the model be part of the model class. So let's go ahead and define a save the model. Keep it simple. Self and file name is equal to models/latest.pt. Nope. My indentation's not working because I did not put a colon there. And we'll do torch.save, self.stateDict, and file name. Again, pretty simple. We could have done this outside the model, but I would just rather encapsulate the functionality that's needed to save and load this model inside the model class itself. And then finally, we'll do def load the model. And in here, we will take self and the same default file name, latest.pt. And we're going to do a try for self.loadStateDict, torch.load file name. And I have too many parentheses. And then let's just go ahead and give ourselves a little bit of logging here. So we're going to say, if we made it this far, if we didn't get into the accept block, we'll say loaded weights from file name. And accept file not found error, because that's the real concern here. Is if there's no file found, we don't want to crash. And print no weights file found at file name. Because that's legitimate. On the first run, maybe you want to load the model if it's there. But if it's not, you want to just carry on. All right, so that should be most of the model class. Let's just stub out a little bit of our agent class to the point where we can go ahead and pull in our model and test it out, or not really test it, just make sure that it loads, that there are no syntax issues. So we're going to do class agent, and we'll do def init. And this will need quite a few parameters. So let's just go ahead and slog through them here. So hidden layer equals 512. Learning rate equals 001. And we're putting these all as parameters so that we can override them later. What we're going to do is we're going to build a train.py that will call the agent class. And in train.py is where you might want to vary your parameters and run different tests. So we'll do gamma equals 0.99. We'll do max buffer size, start out with 100,000 as our default. We will do, and by the way, you don't have to layer them vertically like I am. I'm doing this because I've got my screen blown up for YouTube visibility, but you do not need to. All right, we're going to set eval equal to false. Frame stack will be equal to 3. That's the value I think we end up rolling with. for the rest of it. Target update interval equals 10,000. And max episode steps will equal 1,000. And we want to go ahead and say epsilon is equal to 0. Min epsilon equals 0. Epsilon decay, if I can spell decay correctly, will be 0.995. And our checkpoint pool, which we haven't talked about yet, but we will later, is equal to 5. Okay, so we've got a whole bunch of default params. We're through that. We won't have to type it out again. So let's go ahead and set our device in here. So device is equal to CUDA 0 if torch.cuda.is available, else CPU. And this is probably a good place to stop and run a test. Let's go ahead and import torch. Okay, we've imported torch. We've got our basics for our agent definition. Let's go over and add a train.py. That is going to be our default file that we train from. And then we're just going to say from agent import agent. And then here we'll just say agent equals agent. And that's okay. It doesn't need to be resolved right now. So just to rehash that at this point, we have a train.py that's just importing agent and declaring a new agent. We have an agent that is just stubbed out enough to have an init method. And let's go ahead and just get a printout. Creating agent with device. All right. And then in my case, I am now changing from defaulting to a main.py to a train.py. And let's run. And what we should get, is creating agent with device CUDA 0. If this does not pop up, you are not running with a version of PyTorch that is running on your GPU. And you need to go back and figure out why. Otherwise, when we get into the actual training steps, things are going to be very, very slow. All right. Now that we've got that in here, we can go ahead and do a from model import. Let's see if I can get rid of that. All right, I went and got rid of that annoying little message that was popping up there. Let's go ahead and do from model import model. And then down here, we can go ahead and say model equals model. And let's see what our default params were. So we need an action dimension as well as let's see what all we want to pass into our model. We want an action dimension, we want our hidden layer dimensions, and a few other things. So let's go ahead and pass in our agent.py. We're going to do action dim equals, for now, we're just going to say 3. We'll go back and change that later and derive it more dynamically. But for now, we just want to make sure it works. And then we're going to do hidden dim equals hidden layer. And observation shape equals, we'll do 4. I think that needs to be in that format. Later on, what we're going to be doing is declaring an environment and then passing these things in dynamically. I just want to get the most basic possible test. And then obstack equals frame stack. Okay. Let's see. Did not like observation shape. Must be an iterable, not an int. Okay. So let's go ahead and just code this out the way we're going to need it to work. My basic test failed. So we'll go ahead and say from game import Pong. Okay. And then we're going to go ahead down here and work on, first off, we want this to be self.device. And we'll do self.env equals Pong. Player 1 will be AI. Player 2 will be bot. Render mode will be RGB underscore array. And bot difficulty will be easy. Okay. And that needs to be in, come on. That needs to be in quotes. Okay. So next we are going to go ahead and grab obs info from self.env.reset. We'll set that to self.device. And then instead of observation shape being that, this will now become obs.shape. Oh, and let's see, what did we not like? Okay, so we found a bug, and we found a bug with something that was put together a little bit earlier. So let's go take a look at the game.py and look at the reset method. So when we set up the step method, we successfully returned an observation and an info array. But in this scenario, we also need to do that in reset. So let's go ahead and in here, we're just going to do return self._getObs and then open curlies for an empty array that will represent info. Okay. Hey, expected to have 3 channels, but got 1 channels instead. There's one we can also dig into, and I think I know what's going on here. So this is a scenario where our agent is expecting here. This is another one. I'll see if we can hack real quick to get around it until we've written the code. But if not, then we will just write out the code necessary to make this work. Let's make obstack equals 1. All right, and we are successfully up and running. So why did that fail? Well, it failed because we haven't actually stacked the observations yet. We haven't done anything to do that observation processing. So we know at minimum that and by the way, if it wasn't clear, what I'm running is train.py. So run your train.py, it should call your agent.py, which is pulling in your model and testing that entire stack all the way down. So that's probably as good a time as any to go ahead and set up our frame stack here in just a moment. So we're going to need a couple things. And just to kind of explain again, frame stacking is we're going to concatenate 4 images together that will show frames in order to give the agent a view of what's happening over time. If you don't have that what's happening over time view, then what you end up with is you end up with something where it can't tell which direction the ball's going because there's nothing in the image there's nothing in the observation that would actually show it that the ball is going in one direction or the other. So we're going to do self.framestack equals framestack, and that's just holding our number of frames stacked. We'll do self.frames is equal to, we're actually going to need a deck here, which is a double-ended queue. So let's go to the top and import. Actually, I think, oh, nope, it's from collections. It is not import deck. It is from collections import deck. All right. So we've now imported our deck, and we can do deck maxlen equals framestack, or we'll do self.framestack just to be consistent there. And then we will go ahead and do a process observation. And basically, there's a few different ways you can handle this logically. I have chosen just to pass all observations to process observation, and then to let process observation handle the logic around the frame stacking. We're also going to set up an init frame stack method. So let's go ahead and do init frame stack, and then we'll do our process observation. So def init frame stack self obs and self.frames.clear. And we'll say for underscore in range, because we don't actually need that variable, self.framestack, self.frames.append obs. And this is because we can't have an empty stack of frames. We're going to, need that full all the time. So when a game first starts, we want to go ahead and fill frame stack with, that first frame. It's just going to go ahead and fill it up. Here we'll do def process observation self and clear stack. We're going to default that to false. And then we will do obs equals torch.tensor obs dtype. Nope, not what I wanted to do. obs dtype equals torch.float32. And then we'll say if the length, if len of self.frames is less than self.framestack, then go ahead and do self.init framestack. And then we're also going to say if clear stack self.init framestack. You could combine these into one if statement. I didn't previously because I was doing some troubleshooting and wanted to be able to log when it was getting called with clear stack and when it was getting called, just because of being under the size. But there's no actual reason to have those separate. It is just how the final code ended up working. So if neither of those things are true, we're going to go ahead and do self.frames.append obs. And then we're going to do obs stacked equals torch.cat tuple self.frames dim equals 0. And then finally return obs stacked. And then why is it not? Oh, it's not understanding clear stack because up here I typed clear because that definitely makes sense. Stack. Okay. So we now have a process observation and an init frame stack. So if we come back up here and we say obs equals self.process observation, obs, that should now be a stacked frame. And if we run it, it should fail because this is now a stack of 1 and it's not the right shape. And that is, it does fail, but it doesn't fail for the reason that it should have. Let's take a look at why. Well, it might be because I did not pass in OBS. Okay, so now we're seeing exactly what we expected. Expected input to have 1 channels, but got 3 channels instead. That is precisely what we hoped for. So up here, we can now say self.framestack is the correct thing to call that model with. And we should get a successful, no errors. We get 1 warning, but we get no errors with that. All right. This seems like a good stop point. In the next video, we're going to build out the buffer.py, and then we will, in order to store our replay buffer, and then we will continue on with building out our agent. So until next time. Welcome to part 6 of the Dueling AI Self-Play Reinforcement Learning series. So today we're going to go ahead and dive in to our buffer class in order to store past experiences for the agent to learn from. So let's go ahead and add a buffer.py. And in buffer.py, we're going to need a few imports. So we'll go ahead and import torch. We will import numpy as np, and we will import os. We're going to need all of those. Let's go ahead and call it replay buffer. And in our init method, we will need a few params here. So we're going to do max size, input shape, n actions, input device, output device, which we will default to CPU, and frame stack, which we will default to 3. And let's talk about the input device and output device. So one of the things that you can run into is the performance differences between things stored on your CPU and things stored on your GPU. And when I say stored on your CPU in this context, it just means that things that are in regular system memory. So when you're running something with a replay buffer on CPU, on system RAM, and you are training with on your GPU, of course, then you're going to be basically sending batches back and forth to your GPU constantly, thousands of times a second. And what that ends up looking like from a resource utilization perspective is you'll see your CPU sitting at 400, 500% with multiple cores effectively just sitting there pushing data back and forth, which can be okay. If you're trying to run this on a GPU that doesn't have a ton of memory, then that's the best way to do it, is to store things on CPU and on your system RAM, and then send those things to the GPU as they're needed. If you have the memory on your GPU to handle storing your entire replay buffer, however large that is, on your GPU, then the best thing to do is just push everything to the GPU, and don't store anything on your CPU and your system RAM. And then when you send a batch to the GPU for training, it's just already sitting there in memory. And you're going to see your CPU usage go down to 100%. It'll just be 1 core running whatever the environment is at full speed, and then all of that load goes over to the GPU, which is a lot more efficient, and it's going to run faster. So what we're going to do is we're going to build out this replay buffer class in a way that lets you push data to the CPU or the GPU, depending on your system requirements. So let's go ahead. And honestly, even if you normally work on the GPU, it can be convenient to have system memory as an option. If you want to test something, crazy, like, hey, what happens if I give this thing a million lines of replay buffer across 48 gigs of RAM? Does it improve performance? And maybe it'll run a little slower while you're testing that, but you can test it, whereas you might not be able to if you're forcing everything onto the GPU statically. Okay, let's go ahead and start coding. So we're going to do self.memSize is equal to max size. We'll do self.memCTR, and that is your memory counter, is equal to 0. And then we're going to go and grab an override variable. So I'm going to say override equals os.get env replay buffer memory. Okay. So what I wanted to be able to do is hard code this in one direction in the code base, and then set an environment variable if I'm running it on a system where maybe I want to cut over to CPU or a secondary GPU or whatever we're doing. So we're going to say if override in CPU CUDA 0, which is the first GPU slot, or CUDA 1, then print received replay buffer memory override to, let's go ahead and make that and then we can do override. And then self.inputDevice equals override. Okay. Else, we just set self.inputDevice equal to input device. Okay. Self.output device will always be output device. That's basically always going to be GPU. And then we want to go ahead and start our memory. So this is going to be the standard state memory, next state, action, reward, and terminal or done. So we will say self.state memory is equal to torch.zeros. And in a second set of parentheses, we'll do max size and star input shape. And then here we're going to do dtype is torch.uint8 device is equal to self.inputDevice. For self.nextState memory, we're just going to copy and paste. And let's see why we don't like, because for some reason I typed torch.device or it auto-corrected to torch.device, and that was not necessary. That is not something you can put there. All right, so state memory and next state memory are going to be the same, which makes sense. Action memory, so self.action memory is going to be equal to torch.zeros, and we'll do max size. Dtype equals torch.int64. And then device is equal to self.inputDevice. All right. Reward memory will be very, very similar. So that's going to be, this is one that we are going to do float 32. And input device equals input device. And then self.terminal memory. So the dones, in other words, in this case, it's going to be torch.bool. And again, device is self.inputDevice. So again, our input device is where things are actually getting stored. Okay, We're going to define a can sample method. So def can underscore sample, self, batch size. It takes an int that helps with some of our tips later, bool, and we're just going to return self.memctr greater than or equal to batch size times 10. So what we're doing with memcounter, there's a couple different ways you could do this. You could have a dynamically expanding memory, and then you could, just slowly expand that up to the max size and then cut off entries that are higher than that. I prefer to go ahead and allocate everything right up front, because that's going to tell you in the first 30 seconds of the program running if you have a memory issue, a buffer that's too large, something that's not going to fit on your system or your device. So what we're doing is we're effectively setting the amount of memory that's full to the mem counter. So when we get to the storage section, we're going to define, which we're going to do in just a second, we are going to define an index, and that index will basically step along the buffer until the buffer is full, and then it starts at the beginning and starts overriding. So there will be one space in memory declared that we will then fill up with our data instead of slowly building that up. So let's go ahead and do def store transition and self state action reward next state done, and idx equals self dot memctr. We'll do modulo self dot memsize. So this is the starting, this is what's going to make it effectively start at the beginning. As mem counter continues, your index is going to get to the end and then loop back to the beginning. Self.state memory, idx equals torch.as tensor. And we're going to do state dtype equals torch.uint8, basically the same thing we did earlier. Device equals self.inputDevice. And then we'll do the same thing with next state memory, except over here we're going to call next state and put that in next state memory. And then here we'll do self.action memory index is equal to int action. Oh, that's not what I wanted. And then we'll do something similar with reward and terminal. And then over here, instead of int, we'll do float. And that's just in case you want, a non-integer reward. We're not actually going to use one here. Done. Okay. That looks good. And then finally, we are going to say self.memCounter plus equals 1. Okay, so that's our store transition. So this is what's going to get called over and over again to fill the buffer up. Okay, then we can do our final method for this one, and that is def sample buffer. And that's going to take self and batch size. And here we're going to say max mem is the minimum of self.memCounter, because again, that's going to be the point in the buffer where we're at, and self.memSize. So if memCounter is smaller than memSize, we're going to grab things that are up to memCounter. That's the part that's full. If memCounter has made it over memSize, then we're just going to grab something that's in our available memory. So our batch is going to be composed of torch.randint 0 to maxmem of batch size and device is going to be self.inputDevice and dtype is going to be torch.int64. Okay, so this is going to grab a batch that's a bunch of random numbers somewhere between 0 and whatever this came back with. That's basically what we're doing here. And then we can use that batch of indices in order to pull back our states, next states, etc. So we're going to grab states is equal to self.stateMemory batch and .2 self.outputDevice dtype equals torch.float32. And these are all going to be somewhat similar. So next states, and we're going to do next state memory. Just don't accidentally miss changing one of them, or you'll end up with states getting returned as next states or something like that. And that can be a really confusing thing to troubleshoot. All right, and then rewards is going to be self.reward memory. And in this case, dtype is going to be output device. Or not dtype equals output device. I'm misreading that. For these, we actually don't need to set the data type. We should be good. All right, and then we'll just remove the too much. We'll go ahead and do dones is equal to self done memory. Did I call it that? No, I called it terminal memory. Okay, so we're going to do self.terminal memory batch to self.output device. And then we're going to have actions is equal to self.action memory. And we will grab our batch, and then we'll do self.output device. And then we're finally at a point where we can return states, actions, rewards, next states, and dones. And this is a good time to stop and read through this and just make sure that there are no typos, nothing missing. So we've got batch, torch randint, batch size device equals input. That all looks good. We've got states matching to state, next state, rewards, done, terminal, action, and actions. All right. That all looks pretty good. That looks like it's in a good place. All right. So let's go back to our agent. All right, and inside of our agent, we are going to come down here above the model and under our observation. And we're just going to go ahead and declare self.memory is equal, and really our model here should be self.model. So self.memory is going to be replay buffer. Max size is equal to max buffer size. And actually, let me see. Yes, I did import replay buffer. Cool. Thought I did. Input shape is going to be equal to oms.shape. And actions is going to be equal to self.env.actionspace.n. This is where we get to be a little bit more dynamic because we built this out as a somewhat proper environment. Input device is equal to self.device, and output device is equal also to self.device. So for now, we're just going to run everything on GPU. Okay, it seems like it worked. It seems like we successfully loaded up. Let's just do a quick test to see if it actually loaded on the GPU. So I'm going to import, and I'm sure there are much cleaner ways to do this. But instead of ending immediately, we're going to do time.sleep 30. So we're going to set a 30-second sleep. And our max buffer size is, what did we set that to? Our default is 100,000. So what this should look like is something over here. If I look at NVI top, and what you can see is that 100,000 is taking up 40-something% of the GPU. And this is a 3090, so that's 10 gigs or so. If we kill it, then what we should see over here is we should see things. Oh, hang on. I was looking at utilization, not memory. Let's go ahead and rerun that and see what shows up under memory. Okay, 27%. So 27%, about a quarter of our 24 gigs. So that's where we are with 100,000. The actual amount that we're going to end up training with later is 200,000. So let's go ahead and set that and see where that lands us. All right. So the 200,000 lands us at 10-ish gigs of GPU memory used. So that's okay. That's what we were expecting. If you are running something that does not have that much memory, if it's only got, say, 8 gigs, you do want 200,000 max buffer size. You can try it with smaller. So let's go ahead and see if we change input device from self.input device. We're going to try this a couple different ways. So we're going to do self-input device CPU. And what we should see now is GPU memory is nice and low. But if I sort CPU memory, I get 8.4 gigs used by Python, which is what we would expect, right? We're storing our entire buffer on system memory. Let's go back to self.device. Again, just doing some testing here. So at this point, we no longer see 8 gigs used. We are, in fact, our Python isn't even showing up in the top of our resource utilization here. And then to do a final test, let me go and let's, for me, this is a build.sh. You can obviously do it by hand. But let's go and test our override variable here. No, that's not what I wanted. So replay buffer memory equals CPU. Let's try that. And what we should get is creating agent with device. I don't yet see our, let's see. I left off a set there. Okay, we should be getting a printout from our script telling us that we have that we've built something out with an override. Okay, I think I need to actually do an export. Hey, there we go. Received replay buffer memory override to CPU. That's exactly what we expected. And what we should see now is we should see that we are back on the CPU. We now have 8.4 gigs of memory, not on our GPU. So we have a successful replay buffer. We are pushing it to the appropriate memory. We're able to create it with either scenario. I actually don't want it going to the CPU, so I'm going to save that off. And we will go ahead and delete this time.sleep. And that is probably a good place to go ahead and break this video. In the next one, we're going to go ahead and dive in to filling the rest of this agent class out, and we might even get as far as a training loop. So with that, I will see you in the next video. Welcome to part 7 of the Dueling AI Self-Play Reinforcement Learning series. In this video, we are going to go ahead and get back into the agent class and hopefully get a training loop going. So let's get started. To begin with, we are actually going to go to train.py and get a little bit of housekeeping set up here. So one of the things that you want to be able to do is change different variables throughout the process. So you want to set those variables in the calling script. You don't want to set them in your final class. So let's go ahead and we're going to set up a few things. We're going to do 500 episodes. Later on, this will turn into more. We'll do max episode steps is 2,000. We'll do total steps. Actually, we don't need that variable here. We'll do batch size is 32. That seems to be the one that works the best. Learning rate will be 0.0001. Epsilon will be 1. Min epsilon, I found worked really well a little higher than usual. I would usually set this to 0.1 for most reinforcement learning projects, but this one seemed to work out a little better at 0.15 with the self-play example. I think having it have a little bit more randomness as it was only playing against itself, it helped it a little bit. We'll do epsilon decay, how quickly that randomness is decaying, as 0.995. Gamma will be 0.99. Max buffer size is going to be 200,000. The reason we're setting this to 200,000 and not a million or something else, other than just memory pressure, we want it to be a little bit faster than that 200,000, is we actually want our buffer to refresh as the opponents change. So it's going to start off, it'll be a little bit of a leapfrog. You can think of, if you think about the way that our agent's going to learn. So we'll start off with, you don't have to type this part out, but I just want to explain. We're going to have a live agent, and we'll call this V1. And then we're going to end up with a series of previous agents. So prev agents. And at the very beginning, so at step 1, V1 will just be copied. So it'll be the agent playing against itself. After 100 episodes, this will be V2. And assuming this is improved, this will be V1 and V2. After a whole bunch of episodes, we'll just pretend like it's only up to 3 or 5. This will now be playing against the last 3. So it'll be playing against V3, V4, and not V5 yet. It'll be really playing against V2, V3, and V4. And when V5 can consistently beat these 3, then it'll get added to the queue and we will move. We'll play against then it'll be V6 against V3, 4, and 5. The reason I'm going into that is you actually want a slightly smaller buffer. If you have a massive buffer, then you're going to be down here, running V20 of your agent, and it's still going to be pulling in transitions from version 1 and version 2. And since version 1 and version 2 aren't going to be very good, it's a terrible player at that point. It's just doing random things. The things that your version 20 agent are learning from version 0 and 1 are not great. So you want to kind of stair-step this and make sure that your buffer size supports that stair-stepping pattern. All right. We're going to do a target update interval of 10,000. We'll do checkpoint pool. So this is the number of previous agents that we're going to play against will be 3. And hidden layer will equal 756. All right. One of the things that I like to have just to capture these things is a start time and end time. So let's go ahead and get that in here. We will import time. And down here, we're going to say start time is equal to time.perfCounter. And then at the end, we're going to say end time is equal to time.perfCounter. And then elapsed time is equal to end time minus start time. And then we'll just say training run completed in elapsed time seconds. Okay, let's go ahead and make sure this works. Okay, cool. My train.py is what's getting called. I just want to make sure that I don't have any errors before we go any further. All right, we're creating agent with device CUDA. And it should be exiting. Let's see. I don't recall. I may have added a sleep. Yes, I did. I added a sleep in order to test something in a previous video. And I don't recall what that was. Okay. But we got training run completed in 30.58 seconds. All right. Let's go back to our train.py. Again, just kind of testing things as we go. One of the things that we're going to want to set up is some logging. So we are going to need a name for our log. We're going to do a summary writer prefix. And in the class, the summary writer, the logger, is basically going to, it's going to put out a log with a timestamp on it. The summary writer prefix is really for what we want to capture for information about this run. So let's say you were testing a series of different learning rates. You might want learning rate to be part of your summary writer prefix. So let's go ahead and actually let's make it a suffix. We will do our string here, and I'm just going to call it DQN as the name, and then LR equals learning rate. And we'll do BS equals batch size. And again, in this case, I don't actually care about any of these because I know what parameters I'm going to be playing with. As you tweak params, if you want to try a bigger batch size, different episode steps, a different, epsilon decay, then what I would do is I would add them to this, and then it's going to put them in the name of the logs. If none of this makes sense, that's fine. You'll see how it plays out later. Let's go ahead and pass in all of the variables that we have just finished defining. So hidden layer equals hidden layer. Learning rate equals learning rate. gamma equals gamma. Max buffer size is max buffer size. And again, we're just getting all this out of the way. That way, when we get to coding up the agent, we've got all our variables. We don't have to do any of it later. We'll do target update interval equals target update interval. Max episode steps is equal to max episode steps. Epsilon is equal to epsilon. Min epsilon, so the minimum we want to allow it to go to is min epsilon. Epsilon decay is, of course, epsilon decay. And checkpoint pool is equal to checkpoint pool. All right, so we've got all of those variables out there. We're going to need a call to agent.train, but first let's go make sure we have an agent.train. All right, we do not yet have an agent.train. So let's start defining agent.train. And then we will actually, let's first just run this again, make sure that there are no unknown variables. There aren't. We're finishing in a half a second. That's exactly what we expect. So we're in a good place. All right, let's go down to our train method. So in agent.py, you're going to def train, and train is going to take self, episodes, summary, writer suffix, and batch size. And from a design perspective, you might be wondering what led to putting some of these variables down here in train and some of them in agent, and setting them as self dot, frame stack or frames or environment. There are certain things that I found if you end up in an environment where you need to do multi-step training, batch size, episodes, those have come in more commonly for me, but there's nothing saying that you couldn't put those variables up here. This is just easier for the scenarios that I usually run into. All right, so let's go ahead and define our summary writer. So summary writer name is equal to runs / datetime .now, and we're going to do str ftime. And in this, you're going to have %y -%m %d underscore %h for hours %m for minutes %s for seconds. And then at the very end, we are going to do underscore and summary writer suffix. Okay. And then we will define our writer is equal to summary writer and summary writer name. All right, and it looks like I have not yet imported summary writer or datetime. So let's go ahead and import datetime. And from torch.utils.tensorboard, import summary writer. Okay. Let's go ahead before we go any further, and we're going to go get a call to agent.train in here. So we're going to do agent.train, and if we go back over to our, actually, I'm just going to open this up over here. The text will be a little small. That's okay. All right, so over here we accepted episode, summary writer suffix, and batch size. So over here, we are going to do episodes equals episodes, summary writer suffix equals summary writer suffix, and batch size equals batch size. All right, so let's run this and just make sure we don't get any errors at this point. And again, training run completed in half a second. So we are in a happy place. All right. So let's continue on with our train method. We have our writer. And again, this is just a logging thing. This is going to give us a way to use TensorBoard in order to show logs that tell us how we're doing. And I will pull that up as soon as we have something to log to give you an idea of what to expect. So let's go ahead and say if not os.path.exists models, we are going to os.makeDirs models. And I bet we don't have OS either. So let's just go ahead and import OS. Okay. And that'll be our spot for storing our models. We are going to define a total steps. So this is just going to track how many steps we've taken in the environment. And then we can go ahead and do player. We actually don't need the checkpoint code yet. We'll get to that later. Let's go ahead and just say for episode. Actually, we do need one thing. Best AVG score, best average score is -100. And I'm not starting at 0 because we're actually going to average below 0. So we're going to add some logic later that says something like if score greater than best average score, then update best average score. If you set this to 0, it will never update because it's going to take us a long time to get above 0. So let's say for episode in range episodes. So now we're finally starting our training loop. We will set done to false, done equals false. We will set player 1 episode reward equal to 0. Player 2 episode reward equal to 0. And then we're going to go ahead and call our environment. So obs info equals self.env.reset. I'm going to add okay, we already have our process observation. So we're going to say observation equals self.process observation, OBS, and we're going to pass a clear stack equals true in here. We will set episode steps to 0 because we've taken no steps yet. And we're going to do episode start time is equal to time.time. And then we'll say while not done, and episode steps is less than self.max episode steps. That's not auto-filling. I wonder if we set it. We probably didn't. So let's come up here and just go ahead and set max episode steps. So we'll set that right below model. Okay. So while we are less than max episode steps, we're going to run. And we will do player 1 action. And what we're going to do here, there are a few different ways you can handle this. We could start off right away with self-play. But self-play is a little bit more complicated. It is something, there are more things that could go wrong. So what I recommend doing is actually starting with playing against one of the bots, and make sure that learning works in a basic you against the bot or your AI against the bot kind of environment. Because if it doesn't work there, then it's not going to port over to self-play. So we're going to start out just doing sort of your standard RL loop versus the bot. our environment supports both. And then we will move over to doing reinforcement learning, in a self-play architecture a little bit later. So we're going to say self.get. Ooh, we don't have a get action yet at all. So let's go ahead and work on get action. This, by the way, is the downside of writing code and then waiting a while to talk about it, is forgetting which parts you have completed and which parts you haven't. So we're going to go ahead and define get action is self, OBS, player, and we'll default to 2. We'll need this later. Checkpoint model will be false. Episode will be 0. And eval mode will be false. We'll walk through where we need all of these a little bit later. So let's just say to do flip obs if player 2, to do checkpoint model, and then we can just pick up the basics down here. So if random.random, I bet I haven't imported random, from random import random. Actually, you know what? The way I'm using that, I just need to do import random. Okay. So if random.random is less than self.epsilon, then and eval mode is false, then action equals self.env.action space dot sample. Else, we want to grab our Q values of self.model.forward, obs.unsqueeze, 0.2, self.device, and we want to grab the 0th element. And then action, we can do torch.argmax, Q values, dim is equal to -1, dot item, and then return action. Okay. It also helps if I get all of this on the right level there. And we now have a get action that we can watch. So back up here to player 1 action, we can go ahead and start working through this. All right, so player 1 action. Let's give ourselves just a little bit of space there. We're going to pass in obs. We'll do player is equal to 1. We will do checkpoint model is false. We'll make this a variable later. And episode equals episode. Okay. We can go ahead and set player 1 reward equal to 0. We'll set player 2 reward equal to 0. And then we will do our next obs. We'll actually take the step. Next obs, player 1 reward, player 2 reward. Done, truncated, info equals self.env.step. And we'll be passing in player 1 action. is equal to player 1 action. And then we're just not going to pass in player 2 action. And if you recall, our env step configuration should automatically handle that. It should successfully, go grab an action for player 2 if there is no action selected. So let's go ahead and run this and just see what happens. All right, agent object has no attribute epsilon. And by the way, we're definitely not at a functional place yet. We are at a place where I want to make sure that what we've written so far works, though. Okay, so we're going to do self.epsilon equals epsilon, self.epsilon decay is equal to epsilon decay, and self.min epsilon is equal to min epsilon. Okay, so it's running, it's doing something. It is taking a very long time, though, to do what it's doing. So what we're probably doing at this point is it should, because we don't have any logging, and it is running for, hundreds of steps. So let's go ahead down here and just go ahead and get some of our logging in place so that we have that. We'll do if total steps. Actually, we don't even want that yet. We want per episode logging for now. So we're just going to go ahead and print completed episode in, we'll do episode end time equals time.time. Okay, and then we will say episode time is equal to episode end time minus episode start time. Okay. And then we can say completed episode with player 1 score, player 1 episode reward, and then we will do player 2 score. Go ahead and track both. And episode time will be episode time colon 1F seconds. And over here, let's do episode time instead of episode Tim. And I have to actually close that off. And then we'll also do another print for episode steps will be episode actually, we haven't even tracked episode steps yet. Yes, we are. Yes, we have. But we also do need to add to it every time. So right up here, let's do episode steps plus equals 1. And down here, then we can log episode steps. All right. And I do need to close that off. Let's close this and rerun it and see if we get some results this time. Okay. We are successfully getting results, but we're not getting any real information, and we're not getting, well, we're getting seconds, we're not getting scores, and we're not getting scores because we are not successfully logging. So player 1 episode reward plus equals player 1 reward, and player 2 episode reward plus equals player 2 reward. All right, this is why we test things. Okay, so we now have what is, a mostly random agent, and our agent isn't learning anything yet. We don't have any learning steps. We're not decrementing epsilon. We're not doing any training, but it is running, and it is successfully playing games in about a second per game. And importantly, we also see these scores mirror each other. That's something we want to make sure we see. So if you see, both of them have a positive score, or they have, one of them has a 5 and one of them has a 4, that is inherently wrong. For player 1 to have a -3, player 2 must have a +3. That is how this game is set up. So make sure that those scores mirror each other, whatever the distribution looks like as you're looking at that. Okay, let's go ahead and start working on a little bit more intelligence here. So we've got our player 1 episode rewards. We've got our episode steps. We have not yet here. Let's do a few things here. Let's grab this, grab episode steps and move it down. Let's grab total steps plus equals 1. We need to increment our total steps. That'll be important later for logging. And then right after this self-env step, we need to actually store our transition in memory. So we're going to say self.memory.store transition. And we're going to do obs, player 1 action, player 1 reward, next obs, and done. All right, and let's just, and also before we forget, let's do obs equals next obs after that. And let's just go ahead and run this as is, because this is the first time we've tied the memory in for real, and I'd like to make sure that it is functional. Okay, we are successfully storing transitions, or I assume we are. We obviously haven't retrieved them yet, but we're not. It's not blowing up. It has not errored thus far. So finally, let's get into the training steps. So we're going to say, we can go ahead and kill this off. So for training, we're going to say if self.memory.canSample batch size. Then we're going to do observations, actions, rewards, next observations, dones equals self.memory.sample buffer, and pass in batch size. And the reason I'm not abbreviating obs here is because we're ending it in a plural, and it just obses or next obses just feels like a strange variable name. I suppose I could have also done obs batch, and that would have been fine too. So we need to change some of our dimensions just a little bit. So we're going to do actions equals actions.unsqueeze, and that'll be 1.long. We'll do rewards is equal to rewards.unsqueeze, and that'll be a 1. And dones equals dones.unsqueeze, and that will be a not flatten, float. We will define our Q values. So our Q values is going to be self.model, pass in observations. Our Q state action is going to be Q values dot gather 1 actions. So that is our Q values with the actions that we have selected. We will need our target. So with torch.noGrad, we're going to go ahead and say next actions is equal to torch.argmax and self.model next observations and dim equals 1 and keep dim equals true. And then our next Q will be self.target model. We haven't defined our target model. Let's go ahead and do that. So let's go up here. And we actually need a few variables here that we haven't defined. So let's just go ahead and get them. So for target model, just copy model. And then what we're going to do here is we're going to say self.targetModel.load state dict of model. Except it's not model, it's self.model. And then let's see. And in fact, it's not just self.model, it's self.model.state dict. Okay, so we've loaded our dictionary, and then we also need our self.optimizer is equal to optim.atom, and we're going to do self.model.parameters, and we'll do LR is equal to learning rate. Okay. And we need to go ahead and import torch.optim. In fact, we need to import a few things. So let's come up here to torch. So let's do import torch.optim as optim. And then I think we're going to need torch.nn.functional as f, a little bit torch, not toch. Toch is not a valid import. No surprise. All right, back down here. We now have a target network. Let's see, Q. Okay, we now have our target model. And we can say next observations dot gather 1 and next actions. And then we can say our targets is rewards plus 1 minus dones times self.gamma, not ampersand, times self.gamma, which we need to define, times next Q. All right, let's go back to the top. Let's remember we're on line 121 here. So we do need to go ahead and grab self.gamma equals gamma. Okay. So remember what we're doing here in Q-learning is we're basically getting our predicted Q values, and then we're using our target model as an anchor point, something that is going to lag behind the current model a little bit, provide it some stability. And what we're attempting to do is we're attempting to get the value of the current state in regards to the actual rewards. So the targets are going to be the rewards, and then this is going to see if it's done. This is going to be a 0. So 1 minus done's. If done is true, done will be a 1. That's what we're doing up here with float. So if done is true, done will be 1. So 1 minus 1, of course, 0. So if done is true, it zeroes out the whole right side of the equation because you can't have a future state value if the episode is over. So we're taking our current rewards plus the value of the next value of our state times our discount factor, which is gamma. So what we're basically trying to do is calculate the value of the current state with a calculated value based on the calculated value of whatever the next state is, plus the actual value of the current state. Because if we just scored, well then, hey, the value of current state is 1. If we haven't, then it's, the predicted value or just the predicted value of our next state. So now we need our loss is equal to f.msc loss QSA and targets. And then we finally have something that we want to log. So we're going to do writer.add scalar. And this is basically a way to just add a value to our writer. So the first thing you want to do here is the label. So stats, and whatever you put before the / will become kind of a category. So we're going to put this in the stats category, and we're going to call it model_loss. We're going to log loss.item, and we're going to put that in total steps. So total steps is going to define the x-axis of that graph. If you don't put total steps, or if you just put this as, say, 5, it's going to create a dot on our graph at 5 and never change. So this is going to show that value over time. If we continue on down, we are going to do self.optimizer.0grad. We'll do our backprop step, loss.backward, and self.optimizer.step. Okay. And then if total steps modulo self.target update interval is equal to 0, then self.target model.load state dict self.model.state dict. And our target update interval, of course, is how often we want to update that that secondary or target model. And I'm realizing as well that let's just go ahead and we don't need checkpoint pull, but we can see that target update interval hasn't been used. And that tells me that we need to come down in here and do self.target update interval equals target update interval. All right. Let's go back down to our train method and continue on. So we're actually at a point here where we can go ahead and start logging our scores a little bit more. So we're going to do a writer.add scalar. And it's important to get this right along time with episode end time and the logging here. We're going to do training. Remember, the first section is the category. And we're going to say player 1 training. And we're actually going to end up with quite a few different metrics by the end of this, just because we're building a little bit of a more complex project. That's why I'm being careful to put these in specific categories. So we're going to say player 1 episode reward and episode. And then we'll do player 2 training. And again, these should mirror each other all the time. So let's go ahead and run this and see if we get any errors. Oh, and we did get some errors. So let's see. Torch.CUDA.floatTensor and weight type torch.floatTensor should be the same. That makes sense. They should. So what this means is basically that one of the things we have, either the input is on the GPU and the models on the CPU, or the other way around, the models on the GPU and the inputs on the CPU. One of those two things is happening. So I can see here that we didn't do anything at all with self.device on the model, but we did do it on memory. So let's go ahead and do a to device. And then at the end here as well, we're going to do .to device. And that's going to send both of these, the model and the target model, to the GPU. And again, if you don't have a ton of memory on your GPU and you want to run your model on, or your memory on the CPU, if you're getting any out of memory errors as you're starting up your load here, or your run here, just change this to CPU on output device. But in this case, I wanted to stay on GPU. Okay, let's see. We got another error. 2 received an invalid set of arguments. Okay. It did not like something about what we just did. I assume. Let's make sure that that it's calling it at the right place. So yep, agent equals agent. We're doing it on self.model equals model. And it doesn't like our 2 here. All right, and I think the problem here is that instead of device, I need to do self.device. Let's try it again. All right, and we have a training run successfully going. Now at this point, it should also be giving us some TensorBoard logs. If you have something like VS Code, then the TensorBoard plugin is going to let you see those logs right there in VS Code. If you don't, then you're going to just run TensorBoard. So if I come over here and just close out of my editor, I can do, so the no-hup is going to send it to the background, as will the no-hup and ampersand combination. But the actual command is TensorBoard -- log_dir equals runs -- port, and then whatever port you want it to run on. So I do want to let that sit in the background. Then I'm going to go pull up a browser. All right, I went to a browser. I have localhost :4444, and you're going to want to click on scalars. And then you'll notice over here, it's got every run that we tried as we were troubleshooting, because it, started a bunch of them. What I would do here is just hit toggle all runs to turn them all off, and then turn on our run here. So what you should be seeing over time is player 1 training should start to go down a little bit, or should start to go up, and player 2 training should start to go down, because remember, player 2 is our bot. It should be our easy bot. Let's go see. So there are a couple things that we probably want to check on as we're starting training here. So let's go grab our game.py and see if we had a default. I just kind of want to check. Okay, so our default bot difficulty is hard. And then let's see, as we got into agent.py, if we did anything with, okay, we did set bot difficulty to easy. So it should be capable of learning to beat the easy bot. The other thing that we probably want to go ahead and log here while we're at it, to make things a little bit easier to troubleshoot, is our epsilon, which in fact, I don't think we've even, I don't even think that we have reduced our epsilon. So what's probably happening is we're seeing random playing, and it's not going to get any better. So let's go ahead and right below our training score here, or actually let's go right above. That's fine. We'll keep these things distinct and separate. We'll do writer.addScalar stats/epsilon and self.epsilon and episode. And then down here, again, this should all line up with your end of episode. This should not be inside of the actual episode loop, but it should be inside the total training loop. We want to do a if self.epsilon is greater than self.min-epsilon. Then we're going to do self.epsilon times equals self.epsilon decay. All right, so what this should do is this should slowly decay epsilon. So if we go back, if you're not familiar with epsilon greedy, actually let me just rerun this so it's at least running while I talk. So if you're not familiar with epsilon greedy, we have our get action method. And what this is doing is this is basically saying if random.random, so random.random is going to return a value between 0 and 1. So if random.random is less than self.epsilon, then it's going to take a random action. So at the very beginning of our run, epsilon should be 1, which means we should always take a random action. As we continue the run, epsilon should slowly decrease. So when epsilon is, say, 0.5, what you're going to find is that you will take a random action half the time, and you'll take an action from the model the other half the time. When epsilon is 0.2, then you'll take a random action 20% of the time, and an action from the model 80% of the time. Our final epsilon, our min, is 0.15. So our minimum random action count is 15%. And what that does is that ensures that that is our exploration value. That is how much the model or the agent is going to explore versus how much it's going to exploit things that it already knows about. Okay. Let's see. Looks like we have an error here, and I see why. We have an error because we have not yet properly batched our inputs. So I'm going to take just a moment and find the code for that. All right, and I found my bug. So right down here, self.memory.store transition, we are basically pulling a next observation here, but we're never processing it. So I need to come over here and do next obs equals self.process observation next obs. And then let's see if we're in a happy place. And we may not see it for a few episodes. Perfectly normal because it takes a little while to hit a point where we're, triggering the self-memory can sample. But that is at least running. And what we should see now, let's just focus on our last run here, is we should see epsilon slowly decaying. And as the model takes over training, we're probably going to see a dip. So what I would normally expect in one of these training runs is to see a performance dip as the model takes over, because randomness will actually perform a little bit better than the model in the very beginning. And then as the model learns and performance gets better, we should start to see player one training trending up. So I'm going to pause the video and wait a little while and make sure that is what happens. All right, I'm back after about 275 episodes, somewhere in there. And as you can see, epsilon at this point is around 0.25. And we've got some really good performance from player one here, as it's training against player two, our standard bot. So this is a good place to pause and run your code and make sure everything is working correctly. If you have any training issues at this stage, if you're not seeing training kind of take off in this first few hundred steps, then you do not want to move on to the next section. Doing self-play is, again, it's more complex. There are more areas for something to go wrong than in what we're doing here, training against a bot. And I would rather you stop and troubleshoot when things are simple instead of when things get more complex. So take the time, run it, make sure it's good before you move on to the next video. This is also another good time to remind you that all of the code is going to be pushed to GitHub under tags that are aligned with the series part. So you'll see a tag for that, a GitHub tag to the code as of the end of this video in the video description. I will also post a link to the Discord if you need help. Start by referencing the GitHub, try ChatGPT, and if all else fails, join the Discord and ask there, and I or someone will be happy to jump in and try to help you figure it out. So with that, this has been a good long video. I think we are approaching an hour. I am going to go ahead and end things here. In the next one, we will pick up with a test method. So we'll throw something together to let you, test against your AI that you've trained. We'll put together some eval capabilities, and we will start working on the actual self-play mechanism to allow the agent to play against itself. So I'm going to end it here and say until next time. Welcome to part 8 of our Dueling AI self-play reinforcement learning series. So in part 8, we are going to actually start building out the self-play infrastructure. And I'm going to start with just a little bit of a conversation about the theory here before we go any further. And then the code will hopefully make a little bit more sense. So I'm just going to start typing in a README here. What we're going to be doing. So right now we have a model that is playing against a static agent. So right now you've got model versus static player. And that's a static player that we coded up in a previous video. And the model will slowly get better against that static player. And what you end up with is performance that looks something like this. If you don't have this level of performance at this point, if you're not in a place where your model is learning somewhat, at least up to scoring 9, 10 in the first 500 episodes against the static easy bot, then now's a good time. Go back to the previous video, look at the checkpoints, make sure this is all working before you go any further. So right now we have model versus static player. And what we're going to move towards is we're going to move towards a stable of checkpoint models. So we'll say checkpoints. Again, I'm just typing things out to explain. You don't have to actually code this part. So we'll say we've got a model v1, and then current model is also v1. So we're going to immediately copy our current model to our checkpoint model when we first start. Now, at some point, we are going 100 episodes in. We're going to do this every 100 episodes. We're going to create a v2 model. And if that v2 model is, as good as the v1 model or better, then we're going to check v2 into our checkpoints. And what we'll have is basically a loop. So in our loop, we're going to choose checkpoint and then play current model versus checkpoint. So for every run of our training loop, instead of playing the current model against a static player, we're going to play the current model against one of the checkpoint models. As we go, so let's say our v3 is a little bit better than v2, we're going to check v3 into our checkpoints. And then at some point, we'll have a max length for checkpoints. And let's say our max length is 3, just for the sake of this demo. We'll have our 3 checkpoints. And when it's time to cut v4, let's say that v4 is better than v1. It's the best one, and v1 is the worst. Again, hypothetically, we're now going to have our list of checkpoints will be v2, v3, and v4. And we'll have a couple of safeties in place. So the 2 things we're going to do is we will be implementing a custom checkpoint pool class that is smart enough to reject anything that does not have a score that's at least as good as the previous scores. And then we'll also be doing a check in the training loop that looks for only the top scores. And when we have a new best score, we will check that in. And what we're trying to avoid here is we're trying to avoid clustering all of the models around whatever the latest thing is. Our goal here isn't just to have the best models in checkpoint, but to have the most diverse set of models. In this scenario, we want the previous copies of the model to be able to be a diverse set of opponents that our current model can train against so that it doesn't get pigeonholed into one strategy that works against one model. If you don't do this, if you either just play the current model against itself, what you end up with is you actually end up with a falling performance curve. So the model will learn how to exploit something against itself, and then it will actually get worse over time as it overfits to its own vulnerabilities. So what you want is a large stable of previous models. You want to keep your checkpoints out of circulation, out of being the thing that's being trained. You never want to train your current model against something that's too close to itself for too long. And I know this because when I experimented with this the first time, my initial strategy was to just say, hey, model, play against yourself and train against yourself. And it ended up not being a stable enough opponent to learn against. It ended up exploiting its own, flaws and then going into a death spiral of performance that wasn't great for what I was trying to accomplish. So this checkpoint pool works pretty well. Let's talk about the one other thing that we're going to need to add architecturally. So we need a way to judge performance objectively, or as objectively as we can. You can't really say, because if everything's working correctly, what you should see is you should see that these scores kind of hover around 0. You'll see, the checkpoint models getting better for a little bit. You'll see this drop down, and then this will get better against the checkpoint. And then you'll see a little bit of a wave up and down. But that also means that you can't really tell whether a model is better than a previous one programmatically very easily. It can be unstable. So what we're also going to do is we're going to build an eval function. So every X number of loops, we're going to call eval, and eval is going to play a certain number of games against our static opponents that we built earlier. So it'll play, for the first few hundred loops, it'll play against the easy bot, and then it'll play exclusively against the hard bot. And that's going to give us something that is a much cleaner way to track performance, because again, this is going to bounce all over the place because it's playing against itself. You can't really tell how good it's doing. You can just tell how well it's doing versus previous copies. But using an eval function, that's going to allow us to actually track, hey, you're getting better against some objective opponent. And an important part of the experiment that we're doing here is that we're not including training data from those objective opponents. So the idea is we are training only against our own data, and then we are testing only against our external opponent, which should confirm that our agent is learning generalized skills, because that's really the promise of self-play and reinforcement learning. That's the thing that we're trying to get to, is the idea that the agent should, through only playing against itself, be able to learn generalized skills that work against any opponent. And that is our objective. And you'll actually see that with self-play, we will achieve better, faster results than this score of 9. We're going to easily hit, 20 against the easy bot, and we'll get decent scores, low single digit, but that's fine for what it is, against the hard bot. So with that, let's go ahead and jump in and start coding. So we're going to add a new file, and this will be checkpoint.py. And I'm going to set the width a little lower here. All right, there we go. That gives us a little bit more screen real estate to play with. We're going to import copy, random, and torch. And then from collections, we're going to import deck. Our class is going to be checkpoint pool. And we'll need a couple things. So we're going to define our init method, and we will take in self, max size, and max size is going to default to 5. That'll be our initial number of checkpoints that we're saving. So we'll say self.maxSize is equal to max size. And then the pool itself is going to be a deck of tuple float torch.nn.module is equal to deck. All right. We will have an add method. So def add self model score. So we're going to pass in a score. And again, this score is going to be based on its performance against one of our static models. That's the best way that we can get an objective score over time. So self.pool.append score, and then copy.deepCopy model. I'm going to make sure we're actually getting a copy. Self.pool, it will be deck, and we're going to sort self.pool. Oh, I got too many curly braces there. Self.pool, and for our key, we are going to have lambda x, the 0th element, and reverse equals true. Okay. And then we will trim the worst member of our pool here. So while length is self.pool greater than self.maxSize, then self.pool.pop. And this bit of functionality is important if you just used a regular deck, the oldest thing would fall off, whereas we want to make sure that the lowest score always falls off. I will say there is going to be a little bit of logic in the agent class that makes this redundant, we're going to be tracking the best, overall top score and only adding those. But this implementation does give you a little bit more flexibility if you want to play with different methods. So I'm leaving it in for that purpose. We're going to go ahead and do a sample. So def sample self. And we will say if not self.pool, then we'll raise a runtime error that basically says checkpoint pool empty. Can't pull from it if it's empty. And then we will do underscore because we don't actually need the score value. And we will do zip star self.pool. And I did not mean to put a dot there. So we're going to unpack self.pool. And then we will return random.choice models. All right, so our sample is basically just going to return a random choice from our list of models. And then we need to add a couple of helper methods. So we'll do def len self return len of self.pool. And then we are going to do def best score self, and we'll return self.pool 0, 0 if self.pool else none. All right, and then finally, and this one is optional. If you don't want to type it out, you don't have to, but it is helpful. We're going to write a quick little reporting method that'll print out some of the models that are in the pool. So def report self. We will go ahead and say if not self.pool, message is equal to checkpoint pool is empty. Print message. And actually, this can be a little bit less complicated than it was the first time I wrote it. Print checkpoint pool is empty and return. Okay. Else, if that doesn't fall through, we're going to have rows is equal to blank set. And for rank score model in enumerate self.pool start equals 1. And then we're just going to do rows.append and a little bit of formatting here, rank. And that's going to be a _7. And then we'll do another pipe there and do score _20.2 F. And then that will be the end. And then we can do header is rank skill /n. Gotta love text formatting. Plus /n dot join rows. And let's call this, first off, that should be, let's call this message plus /n. And the formatting isn't super important here, but it helps. It looks nice. So header. Nope, not Heaviside. Message is what we wanted. Okay, so now we should be able to call our report method, and it should print out the current values inside checkpoint pool. So we have a checkpoint pool that we can use. let's go back to our agent. And I'm going to need to set that again. All right. So inside of our agent class, we're going to need a few more things that we didn't have before. So we'll go ahead and say that our checkpoint pool, let's go ahead and define that. Actually, let's import from checkpoint, import checkpoint pool. Cool. And then down here under our target model, we will go ahead and say self.checkpoint pool equals checkpoint pool, max size is equal to checkpoint pool, because that's a variable we took in earlier. And then we'll do self.checkpointpool.add self.model with a score of -100. So why am I doing -100? The initial agent could score as badly as -20. And this is actually one of the problems I ran into when I first implemented this, is I started with, hey, I'm going to store it with a score of 0. But the thing is that score of 0 artificially put there was better than anything else that would come after it for hundreds of episodes. So what ended up happening is nothing overrode it. It would just, that worst initial model would just kind of hang out there forever, which doesn't really do what we want it to do. So we start out with -100, and then this initial untrained model stays the lowest scoring model going forward. So we're going to say self.checkpoint model. We'll default that to none. That's not something we'll set initially. We will also need to set up some eval environments. So up here under self.env, if you recall, I said we were going to have a couple of environments to evaluate against. So here we're going to say self.eval envs is equal to, and then we'll just copy this. And then we're also going to need a second one. And we're going to leave the bot difficulties. We'll take those off. We're going to be setting that later on. But for each of these, I left out a close paren there. We'll make the first one player 1 AI and player 2 bot. And we'll make the second one player 1 bot, player 2 AI. So those are our ENVs that we're going to define. We'll also need to do a little bit of extra code here for eval mode. This will be when we're actually really testing the model. We're going to say if self.eval mode, which should be one of our params up higher. And actually, we may, here, I think this needs to be eval mode, because eval is, no, that'll be okay. If eval, then we want to go ahead and load our model. So let's find down here. Okay, so we're going to say self.model, and then we want to do self.model.load the model. Self.epsilon is 0, and go ahead and return. Okay, and the reason we're returning if we're in an eval mode is because if you go through and create these environments when you're in eval, it's actually going to spin up multiple copies of Pygame. And if you're attempting to, work in if you're attempting to watch a live game, you don't want 4 copies of Pygame just sitting there. It can actually overwrite some environment variables that will mess things up for you. So that's what we're doing. We're just if eval, load the model, return, and don't do the rest of this. I mean, we may have to move some things up, but we'll get to that later. Actually, yeah, frame stack is here. Frames are here. We'll need these up above. No, that seems good. That seems good. We'll find out later when it errors or doesn't error. So let's go ahead and go get down into our train method. And we're going to need a couple of things here that we didn't before. We're actually going to need to work on our get action method. So get action is here. And the first thing we're going to need to do is actually flip our observations if we're player 2. So there's a couple of different ways you can handle making the same agent play, or I'll even say a self-play scenario in general. So we could train 2 completely different agents to play both sides. And actually, let me take a minute and define the problem. So when you pass in, a human understands and can generalize very easily when looking at a game that playing one side of the game is exactly like playing the other side of the game. In general, if you're teaching a person to play chess or something, or checkers, they don't get confused if you ask them to play the other side of a chessboard or the other side of a checkers board. Most people can generalize that, flipping the board around does not make it a completely different game. Your AI can't. It's not that smart. It's not capable of going, hey, this is, this looks different, but I can still take the concepts. It will actually get confused unless it is specifically trained on, something that tells it what side it's supposed to play. So there's a couple of ways you can do that. One method you'll find comes up in some of the documentation people write on these things is setting up an identity channel. So feeding something into the network that says, hey, player 1 or player 2, and then counting on the agent to understand that when, player 1 set and the ball goes over the left, that's a score, but over the right, it's a fail. Or when player 2 set, the opposite. My experiments with that were a little mixed. It didn't really learn well which player was which, but I also had some other issues at the time, so I'm not going to say that method couldn't work, just that it didn't end up working for this project. The other thing you can do, and what quite a few popular RL papers cover is that you can just flip the observation. So because your Pong game is horizontally symmetrical, you can literally just flip the image and fake the agent out and make it think that it's always playing the same side. So that's exactly what we're going to do. Is in get action, we're going to flip our observation. We're going to say, hey, you always act like you're on the right. So let's go ahead and we're going to define a def flip OBS. And that is going to have one line, return torch.flip, and OBS, and dims is equal to 2. And it really is just a one-line function. The reason I am making it its own function is because this is an important enough piece of functionality that I want to let it be somewhat self-documenting. I want it to be very obvious looking at this later that we are flipping an observation. So we're going to say if player is equal to 2, obs is equal to self.flipObs. Obs. Okay. So simple enough. If we're playing player 2, flip the observation. All right. Now we need to do our checkpoint models. So we're going to say if checkpoint model, then we're going to throw a little bit of randomness in early on. So here we're going to, and actually just to make things line up the way we will, we're going to later, I'm going to throw this whole block that we've been playing with into an else. All right, that's the way we want to land. So all of our previous logic was not checkpoint. That was, calling the standard model. So if checkpoint model, we're going to say if random.random. And we'll put that in parentheses just to be consistent. So if random.random is less than self.epsilon and episode is less than 1000. So what we want to do is we basically want to say, hey, if we're in an early episode, let's get some randomness in our checkpoints, because the checkpoints aren't going to be doing anything. So it has to have some random actions, or it's not going to be a good opponent to train against, or even a passable opponent. So we'll say self.env.actionspace.sample. Else, then we'll basically be doing the grab those, copy them up here. But instead of self.model.forward, it's going to be self.checkpointModel.forward. And everything else should stay the same. And then down here, we're just returning action. So get action should be in a happy place now. All right, let's go back to our train method. And we need to make a couple of tweaks here. So instead of just getting player 1 action, we're going to get player 1 and player 2 action. So we can just rename that to player 2 and then pass in player equals 2, and that should be okay. And then here in our self-env step, we are going to pass in player 2 action, not player 2 reward, player 2 action is equal to player 2 action. All right, that looks like it's going to be okay. And it is a little squeezed on my screen. It's a little bit of a balancing act. I'm trying to blow things up enough to where it's really easy to see at a normal YouTube resolution, but that does mean things get a little bit squished. So doing my best there. All right. So here we are now taking action as player 1. If and player 2, we're getting actions for both. But we need to put a little bit of logic around which one is the checkpoint model, because we're just saying that every single time is checkpoint model false, which is not what we want. So let's go ahead and I'm going to go locate my flip code. All right, so at the very top of our train method here, we've got our best average score. Right above that, we are going to add a couple of variables. We're going to add player 1 use checkpoint is false. Player 2 use checkpoint is true. And then for every episode, every time we kick off a new episode in the range, we're going to say player 1 use checkpoint, player 2 use checkpoint equals not player 1 use checkpoint, not player 2 use checkpoint. And it is important to keep these on the same line, because obviously if you split them out, then the logic is going to be a little bit backwards. But what we're doing here is we're effectively flipping every single time which player is using the checkpoint. So we start out false, true, and then we're going to flip to true, false, false, true. So it should flip back and forth as to who is the checkpoint model, player 1 versus player 2, and who is the real model. So we'll go ahead and say self.checkpointModel equals self.checkpointPool pool.sample. Okay. So we now have a checkpoint model that we can play with. This all looks good. Tighten that up a little bit. Done is false. Our episode rewards should stay the same. Our actions we've already updated. We're already calling player 2 actions. We do need to do a little bit with our store transitions. So we want to only store transitions from the active model. So what we're going to do here is we're going to say if player 1 use checkpoint, then we're going to store player 1 action, player 1 reward. Other way around. So let's just copy that and paste it because we're going to need it in a minute. So if player 1 is using the checkpoint, then we want to store the player 2 action. We want to call self.flipObs and store the flipped observation. We want player 2 reward. And then we want to call self.flipObs on next observation. So there are two places we're flipping observations. We're flipping them when we're calling the model, and then we're flipping them when we store player 2 transitions. So we're effectively tricking the training loop into thinking it's always playing as player 1, and then making it an always player 1 loop in the action selection. After we've got that, we'll throw an else in there, and that's where we're storing player 1 rewards and next observations. And this is probably a good place to run the code and see if we have any obvious errors. We're not quite functional, but we should be able to look for problems with our checkpoint. And I'm going to pause the video while it rolls through some of these. All right, so we've managed to make it through a few runs here. I'm on episode, let's see, we did not print out the episode number. We'll have to add that. Oh, no, we did. Completed episode 226. So I made it through a couple hundred episodes. It's doing about what I would expect it to so far. But we haven't done anything to actually add previous checkpoint or previous models to the checkpoint at this point. And we haven't done anything to evaluate our checkpoint models. So the next step is to actually work on our eval function. So I'm going to kill this, and we are going to build eval. So up above, let's put it above train. We're going to define eval self, and we'll pass a default bot difficulty of easy. And then we're going to say for eval env in self.eval envs, eval env dot bot difficulty equals bot difficulty. So we're basically going to just set those difficulties in the beginning of the loop. We'll have an episode reward equal to 0, 0. And then we're going to say for player in range 2 obs info equals self.eval envs player dot reset. So we're basically grabbing an eval environment from our either the 0th or our first index. We're grabbing an eval environment and setting that, grabbing obs and info from that eval environment. We'll do obs is self.process observation. And we'll go ahead and say clear stack is true, because we want a clear stack for starting our eval run. We don't want any images in that buffer. And then we'll say done is false. Episode reward player is 0. Episode steps is going to be 0. And then we'll just say while not done and episode steps less than self.max episode steps, reward equals 0. And this will look a lot like a training run, or a lot like one of our, standard training episodes. And here we'll say if player is 0, then our action is going to be equal to self.getAction obs player equals 1. That's one thing I don't love about this, the way I coded this out, is, because I'm doing player in a 0th index, it ends up being a little funky right here, but it's not the worst thing in the world. And I'll pass in eval mode is true. And next obs reward done truncated info equals self dot eval envs player dot step, and player 1 action is equal to player 1. Let's see, did I not get an action? Oh, I just called it action. That's the problem. So player 1 action equals action. Elif player is equal to 1, then action is equal to self.getAction obs player equals 2, eval mode equals true. And then we'll do kind of the same thing. I'm just going to come copy this because very similar. Okay, and we're just going to say player 2 action is equal to action. And if you recall, the way we built the environment is if you pass in just one player action, the other action is automatically going to default to the bot. So we don't have to manage any of that logic here, and that's why we built it that way. We'll do obs is equal to self.processObservation, next obs. And then episode reward, player plus equals reward. And then finally, we're going to return episode reward 0 and episode reward 1. Okay, so we have an eval function that we can play with. So what are we going to do with that? Let's go down back into our train method. And we are going to have an eval section. All right, so down here around line 195, right under our target update interval code, we're going, oh, I made a change there. I did not mean to make, I think. All right, so tab in to the same level as writer.addScaler. And we're going to grab a couple more log items that we need here. So we want to be able to not just log player 1 versus player 2 rewards. We also want to be able to log checkpoint rewards versus our live rewards. Because remember, it's going to bounce between player 1 and player 2. Different players will be playing each time. So we want to go ahead and basically log, well, I'll just show you. We're going to say if player 1 use checkpoint, then latest reward is equal to player 2 episode reward, and checkpoint reward is equal to player 1 episode reward. Else, latest reward is equal to player 1 episode reward, and checkpoint reward is equal to player 2 episode reward. Okay. We can go ahead then and add some extra lines here. So we're going to add, copy these, and instead of training score player 1 training, we're going to have latest policy and checkpoint policy. This is definitely something I've noticed building out self-play, is that I found myself logging a lot more information because it was just a little bit more complicated to keep up with. And I ended up needing all of this in the course of building the solution. So we're going to say latest policy, latest reward, checkpoint policy will go to checkpoint reward. All right. Then we are going to need a whole eval section here. So under our checkpoint policy, we're going to say if episode greater than 0 and episode modulo 20 is equivalent to 0. So basically, if it's not the first episode and every 20th episodes from there, we're going to do print eval run started. And actually, let's do a little log header method, because we're going to end up typing this a few times and it'll just pretty it up a little bit. So let's do def log header self line print dash times 50, not 500, 50, print line, and then we'll print a closing dash times 50. And that'll put us in a good spot. All right, let's go back up to where we were. Somewhere. Here we go. All right, so instead of print eval run started, we're going to say self dot log header eval run started. Okay. We'll add some dots. To be continued. All right, and then here we're going to say eval env list will be easy, hard, if episode is less than 400, else hard. And the reason we're doing this is in the very beginning, it's really hard to see any kind of performance uplift against the hard bot, because the hard bot is really hard. It is a very difficult bot for the agent to learn against. So we're going to go ahead and include the easy bot so that we can see some early training success and see if things are working. At the same time, once we're up and running, we don't want to waste the time running a bunch of episodes against the easy bot that are just going to be maxed out. Very early in training, it can beat the easier bot pretty successfully, and it's just not useful data. Again, especially when it takes time to generate. These are not free. They take some training cycles. So for difficulty in eval env list, we're going to say player 1 score v bot, player 2 score v bot is self.eval. And I just remembered why we did not do a self.eval here, because this would have run into issues. Okay. Okay. So self.eval, and we're going to say bot difficulty is equal to difficulty. And And that should be all we need there. So now we can go ahead and go writer.add scalar eval score / player 1 v difficulty bot player 1 score v bot episode. And then we're just going to copy that and say eval score player 2 vbot, and then we'll do player 2 vbot. And then just to make sure that we get something in the logs as well, I like to have both. We're just going to print player 1 v difficulty bot and player 1 score v bot, and then copy that to player 2. Okay. And then come in 1 and print eval run finished, saving the model. And we'll go ahead and self.model.save the model. And print model saved. You can tell I'm a fan of logging. And then I'm also going to say self.checkpointpool.report. This is when I want it to print out how the checkpoint pool is going. And then we'll do self.logHeader, and we'll say eval run complete. And I just want to, we've added a bunch of code, we've added some eval stuff, we've added a bunch of eval logging. Okay, we are not erroring. Now again, we still haven't added any code. We've got, player 1 training, player 2 training. At the 20 episode mark should be when we kick in our bot. Hey, there we get our eval score. And we've got eval scores versus easy bot and versus hard bot. All right, and the easy bot, the player 1 scores look right. The player's 2 scores don't. That should not be 0. 0 is actually a really good score against the hard bot. So that tells me that we have a problem here. Let's see what our problem is. So our eval run started. Player 1 versus easy bot. Player 1. Okay, so yeah, those are also coming back zeros. So that is clearly not succeeding at doing a training in eval run. So we've already got player, and it's player 2 in both scenarios. So player 1 score vbot, player 2 score vbot, both calling self.eval. Let's come up here and take a look at self.eval and see what maybe we're messing up. So episode reward plus equals reward. We'll cancel that. We don't need it anymore. While not done. All right, so 4 player in range 2. Let's just start there. Okay, def eval 4 player in range 2. And it's always player 2. So there's something about the, I think I see what might be going on. So here we are doing a reward for player 1. And here we are also doing a reward for player 1. So here we should flip our underscore to that reward. And let's run it again and see what we get. And by the way, if you, because you will stack up quite a few of these runs, you know, this has just been in the course of a few test runs while we've been working on the project. I probably ran this 1,000, 2,000 times while working on the project. You will not want to keep every run you've ever had. Just clear out the runs directory every once in a while. When you hit a point where you want to get rid of all that old data, clear out runs and that'll solve the problem. Okay, we're at 14. Let's keep going. At 20, we should see our eval run kick in. And you can also start to see even now how, you know, latest and checkpoint policy data can start to be useful. Like we can see that our latest policy is already starting to get a little bit better than our checkpoint policy. And, you know, our training wouldn't really tell us this. Like player 1 versus player 2 isn't super useful for telling us how things are actually going. All right, we're still in a flat state. So player 1, let's go look at, yep, eval run complete. Player 2, we still landed in a failure there. All right, so elif, player 1, action is action. This is, something is broken here. So if player equals 1, we want to do player 2 action. We want to grab self envs. We already fixed the reward here. We're calling it with player equals 2. Like this is clearly going to be some kind of variable missing. While not done. Range 2. All right, I'm going to pause the video for a moment and see if I can spot the problem. All right, and it is an indentation issue. So my return statement here is inside the loop, and it needs to be outside the loop. So we're basically collecting player 1's data, and then we're exiting and returning, and that is definitely not what we want to do. So let's run this one more time. And I'm again going to pause while this runs. All right, let's see how we're doing. We're not quite, yes, we have been over 20. And we can see now that player 2 versus the easy bot is 1, and player 2 versus the hard bot is -10, which is much more what I would expect. I'm also, you know what? I've been a little surprised by the -10s, where I was expecting 20. And I think it's because when we were working on the game, we set a top score to 10. So let's go ahead and hop in game.py here and change that to 20. 20 is going to give us a lot more play here. So, all right, so we've changed top score to 20. Let's go ahead and kill this. All right, and we are going to complete, we've got just a little bit more in our eval section here. So at this point, we are evaluating how our agent's doing. We're evaluating our performance over time. The last thing we need to do is we need to go ahead and set up our checkpoint pool evals. And we could bake this into the eval section, but we're not going to, or the eval loop that we just wrote. But I actually only want to update the checkpoint pool every 100 episodes. So we're going to break this out and make it a little bit different. So down here, we're going to say if episode greater than 0 and episode %20 is equal to 0, then we'll do self.logHeader checkpoint pool eval run started. We'll say player v bot total. We'll set that to 0. And we'll say eval EP count is equal to 3. So we're going to run 3 eval episodes, and we're going to total up the scores, and that's going to be what we check into our checkpoint run. So we'll say for I in range, eval EP count, and we'll do player 1 score vbot, player 2 score vbot is equal to self.eval. And in this scenario, I'm only going to do bot difficulty hard. I want the objectively best model, and I don't care about, the visibility data from it. So we'll do player v bot total will be plus equals player 1 score v bot, and then copy and paste that. And we're going to say player 2 score v bot. We'll go ahead and print that. Player v bot total will be player v bot total, and player v bot average will be player v bot total divided by eval episode count times 2, because we're grabbing 2 scores every single time. So if we're doing 3 episodes by 2, that's going to be a 6 eval count. So we're looking for the average player vbot score, and then we're going to say self.checkpointpool.add self.model player vbot average. And I actually thought I had remembered adding some code in here to only check in the absolute best models. It looks like that is not what I ended up doing. That's what happens when you iterate on a piece of code for a month. And we do up here need to say 100. That should have been 100 and not 20. I made it look a little bit too much like the code above. So every 100 episodes, we are going to add the latest, model to the checkpoint by score. Again, the checkpoint pool is smart enough to only add models that are better than all previous models, and then bump the worst model out of the pool. And then finally, we'll say if player v bot average is greater than best average score, then best average score is equal to player vbot average. And we're going to say self.model.save the model. and file name is equal to fmodels/model best.pt. Okay. And then we'll say saved new best model, average score, best average score, higher than player v bot average. Okay. Else print failed to save new best model. Oh, I need an F at the beginning so that we can use variables. And we're going to say best average score higher than player one bot average. Okay. And then at the very end here, we will say self.log header, checkpoint, pool, eval, run, finished. Okay, and I need that 1 over, otherwise it's not going to log out successfully, and that will not give us what we want. Okay. I feel like this episode time is going to not, that could result in some weird, a little bit of weirdness. But I think it'll be okay. That'll be fine. All right, let's go ahead and run this. And what we should have now is at the 100 episode mark, we should go and save our model. And you know what? Let's test this functionality just a little bit faster. Let's say that every 10 episodes, we want a checkpoint model, because I don't feel like waiting for 100 of them. And this is not the best thing for training, but it is going to be the best option for seeing if we're being successful more quickly. Okay, we've hit 8 runs. And we just started a checkpoint pool eval run. We can see we could probably do some better logging around like that this was a checkpoint episode. And that's why the episode time was 19 seconds. It does show us what we need to see though. All right, so the good news is it didn't fail on the eval run. That seems like a positive. It does say that it saved new best model. Yep, average point, score 19. That feels like, okay, I think I see our logic issue there. So player v bot average, we've already set best average score to, yeah, let's do this. Player v bot average higher than best average score, and then we make that change. Otherwise, it's just going to say that, you know, the new average is better than the new average, which is not super helpful. And we can see here that when we print out our list of models, it does have our original with a score of -100, and then it has our new one with a score of only -19.67, which sounds like things are working exactly the way they're supposed to. All right, let's change that back to 100. And this is now the time to go and run this and let it play for, you know, an hour or so and see if it learns successfully. I am going to go ahead and end the video here because this has been an hour long already. In the next video, we're going to come back. We're going to see if this did in fact train successfully. And then we're going to integrate the successfully created models in with our Pong game so that you can watch the thing play, you can test it in real time, you can play against your own agent, and that will be the last video in the series. As always, if you need help, look in the video description. There will be a Discord link. I will also post the code as of the end of this video, so you can go take a look at that tag out on GitHub. If all else fails, post a message in the video comments, and I will try to get you some help. So with that, I will say thank you for sticking with me for this long, for this really fun little project, and until next time. Hello and welcome to part 9 of the Dueling AI Self-Play Reinforcement Learning series. This is the final video. And I'm actually going to start off talking about some metrics and a problem that happened in the last video. So one of the issues, and this is something, a couple things you should fix. So down here around line 150, in the last video, I left a bug in here accidentally, although it does help, where we were consistently selecting actions with checkpoint model equals false. So in your code base, if you faithfully followed along in the video series, you had checkpoint model equals false down here for both of these. And what that was doing is effectively making the agent play against a live copy of itself. And I talked about that earlier in the series and why we wouldn't want to do that. But this gives us an opportunity to see what that looks like firsthand. So this is running, this was a run on one of my lab servers. And you can see what happened here is we peaked, we had great performance a little before 1,000 iterations. And then that performance started to fall off. And by 3,000 iterations, we were down here back at -8. And you can see it kind of started to spike up, but it probably wouldn't have stayed that way. It would have continued this sort of race to the bottom. And this is because while it quickly learned, because it was playing against a rapidly improving agent, it was learning against agents that changed quickly, again, itself. And it was able to exploit small flaws in its own, at least at this point, I'm theorizing a little bit. My theory is that it exploits small flaws in its own gameplay and then slowly sort of pigeonholes itself into certain strategies to where even though loss will, be fairly low, it's not going to get better against diverse opponents like our hard bot over here. So this is what that looks like if you've still got that false. I did post a comment in the previous video to try to head people towards making that change. So if you've already fixed it, awesome. Hopefully you have a successfully trained agent. This is what a successful training run should look like. So this was after making 2 changes. I fixed and set that to false. And then up here in train.py, I set episodes to 3,000, which I think I did in the last video. And then I went ahead and updated checkpoint pool to 5. So we want to keep 5 previous checkpoints, and we want to make that change that we just talked about in the agent.py to set checkpoint model 1 to player 1 use checkpoint, and checkpoint model for player 2 action to player 2 use checkpoint. So make sure you make those changes, go train your model. What you should see is that at about the 2,000 episodes mark, you're going to have pretty good performance at 1,000, around 2,000. You've gotten it to where it's going to be close to that 0. If you keep training, you will sometimes see it go, up to between 2 and 4. I'm not going to keep training though for the purposes of the video. I think we've got the architecture working the way we want it to. But that's definitely something you should experiment with. Experiment with training longer, with different hyperparameters, try different batch sizes, see how it affects training. This is really the point where you start to learn when you either fix bugs or make changes and see how those changes react. So our final piece of code here is going to be to test the AI. And what I would normally do here is I would have a test.py, and that test.py would call the AI agent and let you, watch a training or watch a validation run. But that's not really the paradigm I was looking for here. I wanted to integrate it back into the game and basically allow you to play against your own AI. So that's what we're going to do. We'll still have the ability to play, to just watch it play if you want to, but we're going to actually make the game itself capable of picking up an AI agent, and then using that AI agent as one of the players. So let's get started. We've already done a few things in this area. If you go all the way back to our first video or two, we've already got self.ai agent set to an AI agent, which is defaulting to none. We are going to create a method called, let's go find our get bot move. All right, so there's get bot move. And up under get bot move, we're going to go ahead and say get AI move. So def get AI move is going to take a player, and we'll say if self.ai agent is equal to none, then we're going to raise an exception, because you can't have, can't make an AI move without an AI. All right. Elif player not in 1, 2. So if we try to pass in a player that's not player 1 or player 2, we're going to raise exception. Only players 1 and 2 are valid. And the reason I'm doing some of this is I don't want to end up in a scenario where, hey, we're coming back with zeros or an action of none or something. I'd rather just be very explicit. If the player isn't in the player list or there is no AI agent, stop. Don't go any further. All right, we're going to do obs is equal to self._get obs. We're going to say, so this is where the model gets a little bit weird, where we've got the AI agent obviously, creating versions of the game, but then we've also got the game calling back into the AI agent. So here I'm going to say self.ai agent.process observation, OBS. We're going to set action to none. And then we'll say if player is 1, then action equals self.ai agent.get action, OBS, and we'll pass in a player equals 1. Elif player is 2. We're going to do action equals self.ai agent.get action, OBS, player equals 2. And as I'm looking at this code now, I'm seeing that I could probably just do player equals player, and that would have also solved the same thing. I don't recall why I did it this way the first time, but we're going to be true to the first implementation. All right, so def get AI move, we're basically just getting an observation, we're processing observation, we're saying action is none, and then we're grabbing an action from one of these. All right, let's go ahead and up above our get bot move, we should have our game loop here. And here we're basically going to add another couple of selections here. So we're saying if player's human, grab human actions. If player 1 is a bot or player 2 is a bot, get bot actions. And then we'll say if self.player1 is AI, then player 1 action is going to be equal to self.getAIMove, the function we just defined, and we'll do player equals 1. And then another if, self.player2 AI, we'll do player 2 action equals self.getAIMove, and player equals 2. And as a quick reminder, the reason that these are not if-elif statements for the bot and the AI and the human is that we actually do want the condition to be that both players could be AI, both players could be bots, or we could have any number of other combinations. So I think that puts us in a good spot. We should be able to go ahead and try the game. So let's go to our main.py. If you recall, that's where we kick these things off. And what I'm going to say is I'm going to say player 1 is human and player 2 is the bot. So we're just going to run main.py here manually. All right, and something is definitely driving that left player, but it's not playing very well. In fact, it's playing pretty horribly, which makes me wonder if we are not successfully getting those actions back, because that is not consistent with the, in fact, that almost looks like the easy bot. So let's because that's exactly what I did. I did player 2 equals bot, whereas I should have done player 2 equals AI. I also am missing I'm never actually creating the agent. So let's go ahead and create that agent. I'm grabbing my main.py. So we're going to say agent equals agent eval equals true. Hidden layer equals 756. And those are the only things that we should need to add here. We can go ahead and say from agent import agent. Okay. And then let's go run it again. Oh, one last thing. I need to actually add AI agent equals agent. Okay. We're close. All right. Cannot access local variable obs where it is not associated with a value. Okay, let's go see. What I suspect we're running into here is we probably have an order of operations problem. So we're trying not to create these environments, but we need some information from the environment for this eval step. So I'm actually going to hack it just a little bit. I don't love doing this, and there are probably better ways around it, but I am just going to say observation shape is frame stack 8484. That is the size that we're going to use. And then we're already hard coding action dim as 3. So let's try it again. Okay, we are loaded. And that looks much more like our AI. And you can see, so far I have not been able to get a score in. We'll see if I get one before it does. Reminder that I'm on the right. Ah! All right, it successfully scored twice there. I missed 2 of them. So I would say that our AI training here has been successful. Again, we only ran it for 2,000 episodes. You can go longer and you're going to get better performance. Let's go ahead. And right now, again, I'm playing as green. Let's go ahead and kill this off. And I am just going to go back over to game.py or not game.py. We made all of this modular. So main.py. And we're going to paste that. And I'm just going to say AI player 1 and the human is player 2. Again, player 2 being the purple on the left. All right, so now I'm playing the left. And that does look like our AI successfully loaded and is doing very well. All right, and then if we want to take a look at what it's doing sort of in the eval loop, you can watch player 1 as bot, and we'll do player 1 as AI. We'll be rooting for the AI on the right, and player 2 on the left is the bot. And let's see how that does. Oh, but we did EasyBot. And you can see just how easy EasyBot is for it to beat. We're going to go ahead and update that to bot difficulty hard. And now we should see our somewhat erratic bot on the left playing against a well-trained AI player. And the cool thing about what we just did, so let's kind of go back and look at the project from the top down, is we now have an agent that has never in training played against anything other than itself. This bot that we're watching on the screen right now has never played, as far as it knows. Now, obviously, it does play it in the eval episodes, but it's not storing those memories. So as far as it's concerned, it has never trained against our hard bot. It has only ever trained against old copies of itself. And then while training against old copies of itself, it's gotten good enough to play really, really well against a clearly aggressive, player here. It did just fail there. But again, the hard bot is incredibly hard to play against. It's basically doing nearly perfect ball tracking. So this is really cool. This is, obviously we implemented this in a Pong scenario, but the idea of agents being able to train themselves without, explicitly knowing the opponents they're going to be against, and get this kind of performance, to me is really, really cool. So this is the end of the series. I will post the final code base it'll be in the master branch as well as the part 9 GitHub tag. And if you enjoyed this, hit like, follow the rest of my videos. I do quite a bit of AI reinforcement learning, a little bit of robotics, and some general programming. And if you have stuck with me through this entire series, I think you will probably like the rest of the things that I build. So with that, I'm going to say until the next video.